大家早上好，我们今天是游戏和元宇宙的第2天的论坛，我们早上呢第一个演讲者是 Sebastian， 他是从法国巴黎来的，他是用 Rust 语言写的那个物理引擎叫 Rapier，现在呢他也在，同时呢他也这个 Rapier 这个物理引擎呢也和 Bevy 用 纯 Rust 语言写的 Game Engine 就那个游戏引擎也是有一个很好的结合。同时呢，他今天也来给大家探索一下，就从一个单一的物理引擎怎么做一个分布式的物理引擎，这个也是为了将来在元宇宙这个场景下的一个布局，相当于一个探索。将来的话，可能你元宇宙是一个比较大的一个世界，一个单一的物理引擎可能不能容下所有的这些object， 就这个等等。所以我们现在有请 Sebastian 给大家做技术分享。
我还准备切那个。
Okay, thank you. Okay, so good morning, everyone. Thank you all for being here, and thank you for having me in this workshop. I'm Sébastien Crozet, so I've been working with Rust for quite a few years now, mainly on mathematical libraries, in particular NAlgebra, which is one of the main linear algebra libraries in Rust, and Rapier, which is a physics engine for Rust. So in this presentation, I will have 2 parts. The first part will be about Rapier, so some information on its features, some demos, and some basic usage of the library. And a second part, which is a lot more technical, more theoretical, about distributed physics with Rapier, but also with any kind of physics engine you might want to use. So let's talk about Rapier. So Rapier is a 2D and 3D physics engine. By 2D and 3D, I mean that it has 2 versions, one version for 2D and one version for 3D. But they both rely on the same code, which is interesting because, as far as I know, it might be one of the only libraries with this kind of features, which means when I have to fix a bug or to improve performances, I only have one code base to modify. And it's real 2D physics, so with actual 2D vectors, 2D matrices, etc. It's not just a 3D version with some constraints on one of the axes. So you do gain the extra performances by using 2D. So it's a rigid body physics engine. Rigid body means that all the objects are rigid, so they don't sustain any kind of deformations. And this allows for quite a few simplifications on the maths, and we will see some examples afterward. One of the main key features of Rapier is cross-platform determinism. It means that in any device, you can have Rapier run exactly the same way. So this includes my MacBook Pro here, which has M1 processors. This includes any kind of recent smartphones with ARM processors, or also desktop or laptops with Intel or AMD processors. So it will be cross-platform determinism. So it will work exactly the same on all of these platforms, which is very interesting for example, networked games. And we will see a very interesting demo later. It has AOSOA SIMD optimization. So AOSOA is array obstruct of array SIMD, which means we can solve multiple constraints simultaneously, and also for quite a few operations can be dealt with 4 lanes directly. Right now, AOSOA SIMD optimizations is not compatible with cross-platform determinism, unfortunately. So you have to pick between the two. We have JavaScript and TypeScript bindings. So you can use Rapier from JavaScript and TypeScript. And it's compiled to WebAssembly. But it's a bit more than just a WebAssembly version. So quite a few physics engines out there will just expose a very raw API for their JavaScript version. So it's very difficult to use. But in the case of Rapier, we do have automatically generated JavaScript bindings, but also manually written layers for the bindings, and to have a very more object-oriented and a much nicer API when you're a JavaScript developer. And we also have a Bevy plugin. So here we have quite a few logos. Fireworks is a game engine written in Rust. It's a very interesting game engine because it is quite feature complete. It uses Rapier as its main physics engine, and it has a very, very nice game editor if you want to create your game in a more WYSIWYG approach, like with Unity, for example. Bevy, so you will probably learn a lot more about Bevy for the talk right after mine with Alice. So Rapier has a plugin for Bevy. It's not the official physics engine. There are recently one additional physics engine named Bevy XPBD that you might want to check out. It's very interesting too, based on the XPBD approach from NVIDIA. Croquet is a platform for creating multiplayer games very easily in JavaScript. And they actually are the main reason why Rapier has JavaScript bindings today, and why Rapier has cross-platform determinism, because that's something they need in their platform, and you will have a chance to learn more about Croquet in another talk today. Quicker Game, it's a small JavaScript platform to create very simple games in JavaScript. And Ultimex. So Ultimex, it's a VR game using Rapier as a physics engine. It's published on Steam, and it was written by Resolution Games, which is a very well-known company for VR games. So that's some of the examples that I'm aware of for the usage of Rapier. So let's see a few of the basics features of a rigid body physics engine. So when you want to use a rigid body physics engine, the first concept that should come in mind is the concept of rigid body. So rigid body is an object which cannot be deformed. So because it cannot be deformed, you can actually think of it as a single point with an orientation. And the rigid body in Rapier is everything you need for dynamics. So it's dynamics in a mechanical sense. So it's like positions, velocity, acceleration, forces, etc. But if you just have a rigid body, you can't really do very cool things. Like you can simulate a ballistic motion, like a point in space which will be affected by gravity, but you cannot have stacks of objects that you can hit, which is way funnier. So you want to add a second concept, so a concept of geometry. And this concept is covered by colliders in Rapier. In other physics engine, it might have a different name, like in Box2D, it's called a fixture for example. And with Rapier, it's called the collider. So the collider combines everything you need about geometry. So it has, well, the geometry itself, like square, triangle, circle, triangle meshes, 8 fields, etc. But also things like density, which when you multiply the density by the surface or volume, you obtain the mass contribution of the collider to the rigid body. And collision groups is also a very usual features in physics engine. It's a way for you to ignore some pairs of collisions in the scene. And colliders will be attached to a rigid body if you want the collider to move in space. And by combining colliders and rigid bodies, that's when you can start having very cool simulations, because that's when you will be able to have stacks of objects or objects with an actual volume. But there's one more features we will find in every rigid body physics engine that's very useful. It's the concept of joints. So a joint is here to attach two rigid bodies with each other, and you can create trees or chains or loops of joints. And it's this tool we can use to make very nice effects like ragdolls. In video games, often we have the players which dies, and when the player dies, it will start behaving like it has actual limbs on the floor, and that's where joints can be used. You can use a joint or a set of joints to create ropes or to create bridges, or you can even use a lot of joints to simulate some kind of deformation by using a lot of rigid bodies attached by joints. You will have something that looks like deformable bodies, even if it's actually just rigid. So with these basic concepts, let's see what it looks like in Rapier. So this is the main repository of Rapier. In this repository, you will find two directories in particular, examples 2D and examples 3D. Also examples 3D F64, because Rapier has a 64 floating point version. And if we go in example 3D, you will see there are quite a few demos. And in particular, you might want to run the all examples 3 demo, which is what I will do here. So this first demo uses more advanced features, which is called continuous collision detection, to avoid the fact that very fast object might miss some collisions in its trajectory. In particular, the fast one on the left here doesn't miss any contact. But let's see a much more simple demo. So the convex polyhedron. So here it's a very simple demo. You have a bunch of convex shapes falling under gravity. Quite trivial. So in the code, this looks like this. So because all these demos share the same code base for the main simulation loop, all here will only contain the initialization of the scene. So you will see a rigid body set and a collider set, which obviously are where you will insert your rigid bodies and colliders. We also have impulse joint set and multi-body joint set, but we won't be using them in this demo because we don't have any joint, but they are needed to initialize the scene. That's why they are not mutable, because we won't change them. So when we want to initialize the ground, we have to first create a rigid body. We are using a builder pattern to make this nicer. It's a fixed rigid body, so it doesn't move. It has some initial position. We insert the rigid body into the rigid body set and get an handle. So handles are very usual in Rust because it's a safer way to address your components without having to deal with some kind of pointer issues. We create a cuboid, so it's not called a box because in Rust box is a reserved name. So we create this cuboid for the floor and we insert the cuboid in the collider set with the handle of the parent rigid body, which means our floor will have a fixed rigid body and a cuboid shape attached to it. And if we look at the convex polyhedra, it's actually quite the same code. So we are creating this time a dynamic rigid body, which means it can move. We insert the rigid body to the rigid body set. We create a round convex hull shape. So a round convex hull is a convex polyhedron with round edges, which can, it's in general, it's a bit more efficient to use round convex hull than just convex hull with sharp edges for some mathematical reasons. And we insert these colliders attached to the rigid body parent. So that's this demo. Let's see an example of joints. So we have the impulse joints example here. So it shows quite a few kinds of joints in Rapier. So in Rapier, all the joints are actually implemented as one generic 6 degrees of freedom or 3 degrees of freedom joint in 3D or 2D. And so all the joints are mainly nice interfaces on this generic joint type. So if we start the simulation, here we have quite a few types of joints. We have, on the bottom here, a lot of ball joints. So a ball joint is a joint which allows all the rotations between two objects. We have here a lot of revolute joints, and we actually have joint motors. So a motor is a way to inject kinetic energy in your system, which is how, for example, to simulate a car, you will create motion for the wheels. On the right here, you have prismatic joints. Prismatic joints are joints for one translation movement, and in this case, they are affected by the motors to make the cubes move against gravity. If I restart the simulation, and you can see here that it's quite wobbly, which is something we don't really want from a physics engine. But we talk about this later. Here we also have some revolute joint, but this time we have limits, joint limits constraints, which means they don't keep rotating indefinitely. They will stop at some angle. So the two boxes here will stop falling at some point. And this one is interesting because they actually are fixed joint. And a fixed joint is supposed to keep the two objects tightly attached with each other without any kind of movement. So in theory, it should just look like this flat plane during the whole simulation. But we can see here that it's also quite wobbly. So one very common issues users will have with joints is this kind of wobbliness. It's because a physics engine, or at least a game physics engine, will usually have some kind of iterative force computation for everything, for contacts, for joints. And because it's iterative, it will not always converge to the actual forces they have to create in order to really make the joint constraint correct. So we will have some violations of the constraint. And in this case, we have forces that are too low in order to keep the plane completely flat. And in this case, we have an oscillation between high forces and low forces, mainly because we have these motors which keeps adding energy to the system. And actually, these two joints, prismatic joints and fixed joints, are kind of the most difficult ones to simulate without errors. So what can you do to fix this? Well, because it's an iterative approach, the first thing you can try is to increase the number of iterations for the constraint solver. So the constraint solver computes forces. So with more iterations, it will get closer to the actual realistic value for the forces. So let's do this. Here with Rapier, we have a quite low number of iterations at first because it's more focused on performances. But let's say we go crazy and we use a very large number here. So with this large number of iterations, we can see that the simulation looks much better. The flat plane here remains flat, except at the beginning we do have a little bit of wobbliness. And on the right, the prismatic joints look perfect. And the rest also look quite good. So the problem with having a lot of iterations will be performances. With 200 iterations, which is way more than we typically need in an actual game, we are running with 5 milliseconds of runtime, where compared with the initial configurations, which was 4 and 1, so about 50 times less iterations, we are running in less than 1 millisecond. So we have, as a game programmer, we have to make a compromise between efficiency and accuracy. There's a second way to improve this situation, and this way is substepping. So substepping is that instead of running one physics step for each frame of your game, for example, you will run multiple physics steps simulating a shorter amount of time in the physics world. So here we have a stepping parameter set to 60 Hertz, which means every physics step will simulate 16 milliseconds on the physics world. If we reduce, or if we increase this frequency to reduce this simulated time, maybe by increasing to 240, which means we divide by 4 the amount of physics time simulated, we can see here that the simulation actually looks way better, even if we keep these 4 iterations and 1 iteration. So that's another way to improve the stability of your simulation, by adding more steps. The interesting thing, too, is that each step here will still only cost you half a millisecond. So if you multiply this by 4, because now instead of running the physics engine once per frame, you will have to run it 4 times, you still have 2 milliseconds of computation times, which is still quite much lower than when we had to switch to 200 iterations. So that's an interesting approach. It will also improve the quality of collision detection. You might have less tunneling, so you might not need continuous collision detection. So it's a nice tool. But we also have a third tool to improve the behavior of joints, which is to completely change the way joints are modeled mathematically. So right now, at every frame of the simulation, we are computing forces for each joint. So the forces will try to keep the object together so that the joint constraints are not violated. But instead of relying on forces, we could encode directly the joint constraint as part of the equations of motions of the system, which means that, for example, for this one, which is a revolute joint, which allows only one rotation between the 2 objects, instead of using 12 variables, so 3 translations and 3 rotations for one object and 3 translations and 3 rotations for the other objects, we could use just 1 variable in our equation of motion, which is just the angle between the 2 objects. So that way, we encode directly the constraints in the equations. And Rapier has this concept. So in mathematics, it's called a reduced coordinates approach to models of joints. And in Rapier, it's called a multi-body joint. And if I switch to this demo, so this also resets all the settings here, we can see that with the multi-body joints, everything looks completely perfect. We have a perfectly flat plane here. We have prismatic joints behaving without any kind of wobbliness. And that's actually normal because the constraint is part of the equations of motion. So there is mathematically no way that your joint can be violated. So that's actually quite nice. But we can't really use this every time. It does have some limitations. Because of the way the math works, you cannot simulate a necklace, for example. You cannot simulate a loop of joints. And it also can be quite expensive in terms of computation times. For example, here, for this scene, where everything are multi-body joints, the computation time is close to 4 milliseconds, so kind of close to when we had 200 iterations. But this is an approach very common in robotics more than in games. Usually for video games, people will use impulse joints with maybe a higher number of iterations, but it's still a very good approach if you really want perfect joints somewhere in your game. And you can mix the two in the same simulation. You can have some impulse joint and some multi-body joint. You can even have simulate a necklace where everything is a multi-body joint and just one of them is an impulse joint so that you don't have an actual loop with your multi-body joints. Okay, so this demo application has quite a few other demo, and I won't go through all of them. In the benchmark 2D and benchmarks 3D, you also have some more bigger scenes where you can compare performances with other physics engine, well, just physics currently. So yeah, this is the base version of Rapier. So if you don't use it with Bevy or with JavaScript. Rapier has a set of user guides for the three approaches. So the basic version here, the Bevy plugin, the JavaScript version. And all three versions, we try to get closer to what people are used when using Bevy or when using JavaScript. And if we see here in the Rapier website, here, rapier.rs, if you look at this demo here, this is using the JavaScript bindings for Rapier. And here we can switch to a different demo, and let's take the same as before, which is a convex polyhedron. This time it's falling on a triangle mesh. So we can try something interesting here. So let's say I stop the simulation, restart, and run for a few steps. Stop the simulation. So first we have a debug renderer that you might be interested in. So it's a way for you to be sure that objects in your simulation are actually where you think they are. It's not an actual renderer. It just tells you exactly which lines you have to render, but you can use any renderer you want, except for the Bevy plugin where we have a plugin for this renderer. And so here I stop the simulation. I have this debug info button. I can click it and make one last step. Oh, maybe we are step 199, and let's just one more, 200. Looks better. So here we are at step 200, and what happens here is that at every step, when we have this debug info checked, we will serialize the state of the complete physics engine. And we compute a checksum of this state, so of the bytes for this state. And this checksum is here. And the thing is, the JavaScript version is always compiled with cross-platform determinism enabled. We could publish a non-deterministic version, and it would actually be a bit faster. Quick test is about between 10 to 15% faster, but haven't done it yet. So right now it's always cross-platform deterministic, and if you go to the Rapier website, to this exact same demo here, and if you make sure that you have the same version of Rapier here, and if you run this simulation until step 200, you will see the exact same number here, even if you try it on your phone, on any kind of recent computer. And that's how deterministic this is. Every single bit in the physics state is the same on all the platforms. All right. So now this is the general architecture of Rapier. It's quite traditional in its architecture, in that we have collision detection, we have force calculation, so yeah, force calculation with PJS is projected Gauss-Seidel, integration and collision detection. So we have two collision detection steps, because the first one is more about collision detection between objects which were moved by the user between two steps. And the main collision detection part is at the end here. And we might have a loop here for continuous collision detection by slicing time into smaller chunks based on how fast objects move. Aside from this main physical simulation pipeline, we have a query pipeline which is responsible for all the scene queries, so raycasting, shapecasting, etc. And we have a character controller and vehicle controller, which are here for you to create a character or a vehicle in the game. And it's based on a kinematic body, rigid body, which means it's a rigid body you have a total control on, completely ignoring any kind of physics rule, which is usually what you want in a game, because you don't want your player to be affected by very realistic physics. And these controllers are based on raycasting here and shapecasting to make sure they don't go through any kind of obstacle. All right, if you want to take a look at the user guides, we have the links here. It's just the same thing as I was showing before here. Okay, so that was Rapier. It has a lot more features than what I showed. It also has cohesion group, continuous cohesion detection, all sorts of different shapes, etc. So you can explore everything in the user guide. Now let's talk about distributed physics. So distributed physics here, I won't cover the complete topic. I will cover only one typical problem you might face when working on distributed physics, and with a proposal for a solution. And again, this applies to any kind of physics engine. I'm obviously testing this with Rapier, but you can use anything you want. It doesn't even depend on the cross-platform determinism feature. Maybe it could to improve it further, but I don't know. So why would we want to do distributed physics? Well, the main idea is to have multiple Rapier instances contributing to the same physics world. And these instances may run on multiple machines. And the goal here is to simulate as many objects as we want to scale infinitely for a very, very, very large open world game or very, very large metaverse. And I want to distinguish between two use cases. The first one is to simulate a very large number of objects, but they are not all interacting with each other. Here we have a lot of individual stacks of objects. And yeah, we do see some gaps between the objects here. So that's the typical thing you will find in video games, which is objects which are not part of the same huge pile. In video games, when you move through the world, you will sometimes observe some physics interactions with your environment, but we won't have one huge stack. And on the other hand, you might want to simulate a lot of objects in a very huge pile of objects. And this one is more interesting for animation of scientific computing when you want to focus on one very small object or one behavior in your scene, and you want to simulate this very accurately. So in our case, we won't try to solve this problem. We won't try, for example, to segment this system into multiple parts and have this system simulated by multiple machines, because that would be very difficult, because you have to involve a lot of communication within your constraints resolution loop. Because here, force computation is a global problem. The force applied to this cube on the top is actually dependent on the force applied to this cube on the bottom. So it's really a global problem. Here we can already see some independent chunks of works, because each pile here are independent from a force calculation point of view. So we will mainly focus on this one. So the general idea here is to apply some spatial subdivision. And we are using a grid-based subdivision. So we have this regular grid. It's very implicit, regular grid, and also a sparse grid, because we won't represent every single cell, because our world is supposed to be infinite. And we will say that every physics instance will simulate one cell of this grid. So here we have 28 cells, if we don't count the cells outside of the screen. And the first instance will simulate this cell will be simulated by a different instance, etc. Which means that the first instance here will simulate all these small stacks, and all the other instances will have no idea that these stacks exist. So in this case, it's quite easy. We could run this simulation, and it would work directly, because all the objects are quite nicely aligned. But we could have something like this. So here we have 4 regions. So we zoomed into 4 cells in our grid, and we have 2 objects, a blue one and an orange one. So based on what I just said, the blue one would be simulated by C, and the orange one would be simulated by D. And D would have no idea that the blue object exists, and vice versa. And now we have a third object, which is the green rectangle here. And now we have a problem, because the green one intersects all the regions in the scene. So the question is, which instance of your physics simulation should simulate the green object? You could think that A should simulate it, because I don't know if it crosses A. But A only sees the green object, doesn't see the blue and the orange one, because they are handled by different Rapier instances. They may even be on a different computer. So A will see the green object and apply gravity, and because we don't have the blue and orange objects, it will just fall down, which is incorrect. And the same applies to B. For C, it's slightly different, because C knows about the blue box. So it will create a rotation here because of the contact point between the 2 objects, which is also incorrect. And for D, it's the same thing, but rotating on the other side. So any choice here is actually incorrect. And we could actually try to simulate the green object with all the regions and try to merge the motion information. That sounds quite complex and not valid from a mathematical point of view. So we will do something different. We will work with a concept of island. So in physics engines, the concept of island is quite common, is a way to group objects into groups that interact with each other. So here we have 3 islands. The green one is just one object. The blue one is 4 objects which are touching each other. So the green and blue are not part of the same island because they are disjoint here. And even if we had a floor below them, it wouldn't merge the two islands because a static object does not transmit any force. Same thing with the red object. And we will define a total ordering between our cells. So in grid coordinates, we could use Cartesian coordinates. We would have 0, 0 cell, 1, 0, etc. And if we focus on the gray cell, so the 0, 0 cell, everything that's green is considered greater based on this ordering system, and everything that's orange is considered lower based on this ordering system. So we will take one step further to simplify our problem, which is to use bounded boxes. So each island here is simplified as one single box, which encloses everything. So we don't have to deal with every single geometry, which might be quite difficult if you have complex geometries like triangle meshes or 8 fields. So we have boxes for islands and we have ordering for regions. Now, if we have our islands in the physical space, we will have maybe something like this. One island can cover multiple regions. And we will say that an island is entirely simulated by a single region to keep the mathematical correctness. And this region will be the greatest among all the regions intersected by the island. So for the green one, it will be simulated by -1, -1, because it's only intersecting -1. The blue one is intersecting 2 cells, and the greatest cells is 1, -1 here. So it will be completely simulated by 1, -1, and the orange cell here will completely ignore existence of this island. And the same thing for the red islands will be simulated only by 1, 1. So this is, if you consider a static picture of your scene, you will subdivide your workload this way based on which island is intersecting which region and which region intersected is the greatest. So you get something like this. Here we have one color per region, and you can see that each group of objects has the same color. So we don't have here, we are at the limit between red and blue, and we don't have something that's half red and half blue. So the complete island is simulated by the same physics sensors, so we don't have any problems in terms of force computation. Now, because we don't have just a static scene, we have some movements. So we have to deal transition from one region to another. So for example, here, if this blue object moves, it will have to be moved from 0, 0 to 1, 1, because it started intersecting the greater region 1, 1. And here we have a more complicated approach, a complicated configuration where the blue object will start interacting with one object which is managed by 1, 1. And this is complex because 0, 0 has no idea this black box exists. So we define a watch set, which is a set of bounding boxes that exists only at the geometric level, so we can detect this case here. So we can discuss more about this case after the talk if you're interested, but don't have a lot of time left. So by taking into account this system, we can, oh yeah, and this is the case if we intersect this one, which is a task 2, 1, 0. So we can start move this scene here, and we can see how the island change from one region to another as the complete scene rotates. And again, when it changes colors, so when it switches from one region to another, it completely changes. Every single box in the complete island will change. So this is an idea of the implemented infrastructure. We have a set of clients, so to visualize the scene, a partitioner, which is responsible for managing all the instances that will run the simulations, and the runners, which are just a program running the simulation in a loop. What happens is that when the client starts a simulation, it will asks the partitioner to insert the object. The partitioner will, based on the object geometry and position, it will initialize a few runners, creating a mesh of runner. And to handle transition from one region to another, we will have communication directly between the runners. And this communication is based on Zeno, which we also use for other purposes like time synchronization. And we have our black boxes for the watch sets, which are inserted into Redis. And when an object moves from one runner to some non-existing region, it will ask the partitioner to create this region with an associated runner, which will fill the mesh, so we never have an object not simulated by anything. Okay, and yeah, last we have the positions which are also stored in Redis, so we can read them from the client, but this is not very optimized, this part. This part is not very optimized. I haven't really focused on this yet. All right, so we do have a few more steps to improve distributed physics. We have to think about the allocations of resources, like when a runner doesn't have any more work, if it doesn't have any objects in it, or if all the objects are just staying immobile. We want to stop a runner. We have scene queries, shape casting, ray casting, inside of the scene. So how do we make raycasts cross regions, and user interaction and collaboration. So here you have a few links for Rapier, the Rapier website, the Rapier repository for the base library, the JavaScript bindings, and the Bevy plugin. And Stadium is just a testbed I use for testing the distributed physics. So it's something very simple. You can draw some object here. You can move objects here. You can start the simulation, and you can grab some objects. You can look at some of the properties of the objects. Yeah, it's a very basic physics sandbox. Some of the buttons don't do anything, like previous undo and redo don't do anything right now. And you can import a mesh. You have some. The built-in scene are just the things I use to test the distributed physics. So if you want to try it, it has a README. You can try it. It has a standalone mode and distributed mode. Okay, so that's it for physics. Thank you very much for being here.
Thank you, Sebastian. 谢谢Sebastian 给大家一个非常精彩的讲解。看大家有什么问题啊？那个 Sebastian 也是从百忙之中跑过来的，他本来应该是他本来应该是在休假中抓过来了。Some questions.
请问就是这个物理引擎会考虑支持现在主流的一些其他的游戏引擎，比如说 UE 和 Godot。
He's asking you if other type of Godot or others.
Oh, okay. Yeah, so right now, I don't really have plans to support game engines which are not written in Rust directly. So for the special case of Godot, I know some people have been working on some support to integrate Rapier. But yeah, right now I don't have a plan for that. It really depends on the demand, really. So yeah.
Okay, thank you.
这basically 就是说，因为Sebastian也是一个叫什么开源开发者，他的能力也有限，他就这么多，他就一个人，加上一些，他主要还是靠社区来做这个事儿啊。社区，你们如果有感兴趣的，那么他自己呢是 focus 在 Rust 语言上，但你们如果感兴趣的，你们也可以做这个 binding 到别的游戏引擎上去，好吧？
And
我感觉 Alice 好像有话要说。
to add to that, when we have to support a new language, it's actually a very large amount of work to rewrite nice bindings, which is kind of the main reason why it's so difficult to handle game engines which are not written in Rust.
So I can actually answer, just from the Bevy side, I can talk a little bit more about how are people using Rapier in other game engines, because the users talk about this stuff, and there are experiments working with Rapier in both Godot and in Unity, but it's very low level, and it generally involves grabbing the world state, exporting it into the Rapier state, doing all your physics there, and then pulling it back out. Like Sebastian said, it's not nice, and actually writing those bindings would be quite a bit of work. But you can do it, and there are people trying.
对的，那个还是要靠社区的力量啊。今天同学们来这么多，要靠大家。
I want to get some plan about work's future. Yeah, yeah.
Okay, roadmap, right?
Yeah.
Future.
Yeah.
Works.
Yeah, so right now I'm mainly focusing on stability because Rapier has kind of all the features you might expect from a game physics engine. So I want to maybe switch between stability phase and runtime optimization phase. An additional feature would come mainly from community requests. And in terms of distributed physics, well, the next steps are what was in the last slide to improve the system.
看看大家还有什么问题？谢谢Sebastian。最终还是要靠大家社区的努力啊！希望你们都加入他这个 Rapier 这个社区，所有东西都是开源的，都是在那个 GitHub。那我们现在就是一个茶歇时间，我们15分钟以后，那个 Alice 呢会来讲一个新的用 Rust 语言构建的那个 Bevy engine， 主要是讲那个 ECS 的部分。好，现在大家休息15分钟。
like you don't have lapel wings. Oh, lapel wings with like shell. Yeah, I just have one. Okay, that's fine. I often like to paint on and do while I talk, so that's fine. It's fine. I can stand here. It's a little. It's kind of going off to the side. Yeah. I don't know if I can do that. Okay, so yeah, that looks like that's working now. Yeah, okay, I don't know why that looks like here. Okay, perfect. Yeah, it's this is using Google Drive.
尊敬的各位来宾，本次会议即将开始，请您尽快就座，并将手机等通讯设备关闭或置于静音状态。谢谢您的合作。
Ladies and gentlemen, the event will begin shortly. Can we please ask for you to kindly take your seats? We would like to remind you again to switch off all mobile phones and put electronic devices to silent mode. Thank you for your cooperation.
感谢大家查询之后又我们来继续分享那个 Game and Metaverse 这个论坛的第二个主题。今天第二个主题是 Barry 今天由那个 Alice， 她是从加拿大赶过来，她是Barry 社区的一个重要的一个 maintainer， 她今天主要讲一下。我们 ECS system 在 Barry Engine 里面，那个 Barry Engine 里面那个 ECS subsystem 是，做的，我觉得是做的非常好的。好，我们现在请 Alice 来给大家分享。
Hi there, I'm Alice. I'm one of the maintainers of Bevy. So, Bevy is one of the most popular Rust game engines, probably the most popular, and it's fully open source. We have thousands of users, we have hundreds of contributors, we have a thriving ecosystem of people doing strange and unusual things that I never thought possible. And as for me, I'm a maintainer. I help run the project, I help make it better, and a lot of my time is spent focusing on the ECS specifically, but also on making our documentation better and on managing the project and making sure everything runs smoothly. I spend a lot of time talking to users about their confusions and their needs, and I'm going to be using that experience today to try to explain how Bevy's ECS system can really work to meet your needs, rather than just being a tool you reach for performance. So, if you don't know about Bevy, our goals are to make a highly modular engine where you can take only the bits that you want and keep the rest, where you can whip out the physics and replace it with your own physics. You can whip out the rendering, replace it with your own rendering. You can write your own first-class networking solution without needing to go and change the source code of the engine. And do generally very, very weird things with it. We're written in Rust, so it has to be blazing fast. And right now, but I think in general, we're going to be focusing on a code-first approach, where rather than using a WYSIWYG GUI to go and change everything in the engine, it's all just code. It's high-quality Rust code that you can test, you can maintain, you can hand to programmers, and for them to be happy and comfortable with it. But similarly, we want to support larger teams with artists, with animators, with audio technicians to have a high quality asset reloading, hot reloading, and strong tools in the future. And the thing that sets Bevy apart from honestly a lot of its predecessors and a lot of competitors is that it's ergonomic. It's very comfortable to use. It's a joy and a delight to program in and to work with and to read. And to do that, we actually used ECS, this crazy structure of arrays performance tool, and used it as a central paradigm to define the whole engine around it. So I want to talk about how we did that and how it actually works, because a lot of people say ECS is a tool that's only supposed to be used for performance, but I don't think that's the case. So let's talk about some basic definitions for those of you who haven't seen ECS before. So ECS stands for Entity Component System, and there are three key parts to it. So first you have the entities. So the entities, so you can kind of think of this as a messy database or table, like you see over on the right, where you have in the rows position you have which entity it is. In the columns, you have which components, which data do they have. And then the entities basically just act as unique identifiers for those rows. You have the components, which will store the data, and then the systems, which will operate on all entities that have matching sets of components. That's the fundamental architecture, and it's very fast. But if that's all you've got, people will say, this will never work. You can't write an entire engine in the ECS. This is horrible. Because writing ECS code is terrible. If you've used Unity's dots, if you've used systems that came before it, they're often very heavy on boilerplate. They make the performance sensitive details very obvious, very in your face, and it's fundamentally too complex, too onerous and frustrating for the gameplay programmers who just want to like hook up something to a door, and when the door opens, the boss spawns. And moreover, when you're using this previous generation of ECSs, you're constantly stumbling over these little tripping blocks. There'll be little things that you want to do, and you're like, how the heck do I do that? And the answer is, oh well, we didn't include that because it's not essential to make the physics system that we wrote this ECS for go fast. And so their opinion is, why would you use ECS if you don't need the performance? And I agree with them. If you have a last generation ECS, don't use it if you don't need the performance. This is a bad idea. But we're not the last generation. Bevy, along with the Flex and a couple of other modern engines, are an entirely different beast. I would call them the next generation of ECS. So something that you get a lot of the time is you'll have ECS as a component of an engine, where you have some sort of object-oriented layer, and then you have this ECS thing, and you try to stick them together and use the ECS only for like the heavy performance-intensive, embarrassingly parallel parts of it, right? But this causes a lot of pain. And fundamentally, this causes a lot of pain because they are different, not because either part is bad. Because if you've worked with complex systems, complex software systems, if you have two different data models and they need to talk to each other in complex ways constantly, you're going to have all of your pain is going to be concentrated right at that translation boundary. And you'll have boilerplate, you'll have bugs, you'll have performance overheads, you'll have issues where where people just don't know both systems. You'll have things where something that you thought wasn't performance sensitive, you got a benchmark, and you say, oh no, this dialogue system is now in our hot loop, oh god, and then you're like, okay, well, do I cut this dialogue system, or do I rewrite it entirely in a different language? And that sort of translation adds a lot of time and a lot of friction and a lot of pain when you're developing big commercial projects. So as a result, because you have these hybrid systems where you have the object-oriented or whatever other paradigm, in addition to the ECS, people don't solve all of the tough use cases that to make ECS good enough. Because while it solves the parallel physics loop, then that's fine. So Bevy has decided that, okay, you know what, this sucks. We're gonna go and we're gonna commit to ECS. We're gonna say, what if everything was ECS? Which, you know, sounds crazy. But there are reasons for that. So ECS is fundamentally about cache locality. It's data should live beside its neighbors, and if the data lives beside the neighbors, you can make your code go faster because you're not jumping around all over the place constantly. But it's about a lot more than that. So if you have everything defined as components, and the components define what behavior applies to each entity, it becomes really easy to write gameplay systems for your game designers that create emergent behavior, like you might see in Dwarf Fortress. Or if everything is ECS, you have a unified control flow where everything follows the same paradigm. It's easy to learn, it's easy to reuse, and it's easy to optimize because rather than optimizing each subsystem of the game, you just work with upstream and make all of the ECS stuff go faster. If you have everything that's living in a single data structure, the world we call it, you have really easy serialization and deserialization. You say, just grab this object, just write it to the disk. There's no custom serial, like Bevy's save, you can write generic save game libraries in Bevy, which is something that is, that's almost like inconceivable in other places. You have this, in ECS, you have this notion where you should decouple your behavior from your data, and it leads to cleaner, more maintainable code. But with Bevy, the thing that's really cool about ECS is its dependency injection, where you say, in this code, I want this data, and please give me this data. And rather than having to plummet down all the way through layers and layers and layers of function arguments, it just magically hands you the data that you want. And this is really like the star feature. And if you have all of this information about what types and data you need at each time in each system, the borrow checker is happy. But more importantly, you can have all of your systems running in parallel with each other based on what data access they need. And that's all defined at the type system level. And your systems just run in parallel with each other in a way that's guaranteed to be safe. So let's talk about, the rest of this slide, let's talk about some problems that you might see when you're trying to adapt a previous generation ECS to write your entire game in it, and some solutions. So here's an example, a couple of examples. One of them is from Amethyst on the left, which is a previous generation Rust ECS, and the one on the right is Unity. And there's a lot of arcane symbols here. There's a lot of repeated boilerplate that you're writing over and over again. And this sucks, and it makes your developers unhappy, it slows them down, and it makes people afraid to use your tool. And Bevy's solution is, we're going to go and we're going to sprinkle a little bit of magic pixie dust from courtesy of the Rust ecosystem to make it just work. You write a function, which is just a function. There's no macros, there's no annotations. It's just a function. You set up your function arguments, and you say, okay, we need this type, and then the ECS will look at those types that you put in your function arguments and say, oh, you want this data in this system, and then when you add it to your schedule, it will just fetch that data out of the world and pull it into that system and run it every frame. And it's all powered by Rust's fantastic trait system, fundamentally. And you'll have things like automated caching of queries. So then from frame to frame, everything will continue to be fast. So suppose we have an ECS and we're using it to define behaviors, and we say, okay, we want to. The classic example is you have everything with a transform and everything with a velocity, and then you make it move like that. But the data that you have and the data that you actually need doesn't always match perfectly to the behavior that you want. So like a player-shaped entity may look a player entity may be shaped very similarly to an enemy entity. They may have exactly the same actually useful data, but you don't want to have your players behave exactly the same way as your enemies. And we could go and we could store something that says, okay, here's our character type component, and then we'll go and match on that, and we do things that look an awful lot like object-oriented programming. But this is going to make your code slow, and it's going to make your code messy. So in Bevy, and frankly, in almost every ECS, we have two components, two ideas that really help with this. So the first is we have marker components. These, or sometimes called tag components, they don't hold data. They're this new type, like that struct enemy, and it doesn't hold any data. It just is a type, and that's what it does. And we use these data list types and we insert them as components, and they're used to differentiate between entities that look the same but actually need to behave differently. And this becomes really powerful when we combine it with our query filters. So you can see down below in the query ref life with enemy that you can say, I only want the life data, but I want to restrict it to the enemy, to those entities that also have the enemy component. And so you get to have some level of you get to have really fine-grained, powerful control there, where the data that you need is separate from the matching set. So one of the other problems that comes up a lot when you're working with pure ECS is, okay, well, where do I put the things that don't really seem to make sense as entities? There's only ever going to be one of them. Like, do I store my game score as an entity? Do I store like how much lumber I have? Do I store like abstract things like tasks pools or audio handles like in an entity somewhere? And like, rather than saying, okay, we're gonna go and make a custom like game object, mega object, it would still be nice to store this all in the ECS because then we get all the benefits, and especially the dependency injection. So Bevy has a concept that it calls resources. Resources are really easy. They're just global singleton data. It's, I only want one copy of this and store it in the world and then give it back out. And it's defined like everything else at the type system level. And they work exactly the same as entities, as components, except they're not stored on an entity. And but similarly, you may have things where you want it to be an entity, but you only ever want it to be a single copy of that entity. And you could loop over your list of length 1, but this sucks and it's confusing. So we have a really simple API called query.single, and it says, fetch me the first object in this list and give me an error if there's not exactly one of them. And it's incredibly useful. And we spent a while debating whether we should add this because it's like, okay, well, why should we use this versus making something a resource? And the rule of thumb that we as a community have come to is that if it shares behavior with other entities, make it a singleton entity. Otherwise, make it a resource. So fundamentally, you have a lot of the things you might want to do with an ECS are often more complex than you might expect, especially as you add features and you might refactor. And the tutorial code often makes it look so easy, where you have a bunch of entities that you want to all treat the same way, and you have a nice, clear querying rule. But what happens if we want to have something that can branch, that can be composed, that can be powerful and expressive? Oh wait, we're making a query language. This is just a database query language. How do we do database query languages? And the answer is we use the type system, because of course we use the type system. We're going to go and we're going to write a query domain specific language in the type system. And there's all sorts of really cool things you can do with this. You can say, give me an option, ref t, which is to say if this component exists, return its value on this entity. Otherwise, give me none. We can have has t, which works the same way, except just returns true or false, and we can just branch on that. We can have things like any of. We can have or combinators. And then we have even more exotic things like trait queries, where you get all the components of an object that implement the specific trait, and it returns them as a trait object in your iterator. And this level of expressivity and power, it's hard to really appreciate until you've gotten yourself into one of those corners where you're like, oh man, if only there was a way to ask for exactly this data in exactly this way without having to go and rewrite everything or add some stupid hack. And by expanding the query system beyond really simple filters and component data requests, you have such a more powerful tool in a way that the previous generation of ECS doesn't. So here is here's a pretty simple problem. So suppose we're writing a collision detection problem, and we run our queries. We have two entities that have recorded, and how do we know which entities those were? Because if we're just allowed to ask for component data, we don't know which entities they are because it's just anonymous data. So what you can do in Bevy is you just add entity as another query item as if it was a component, and it'll just return that in your iterator like everything else. But this becomes a lot more powerful is when the question becomes how do we actually use these specific entities that we recorded? How do we actually do anything with that? We could go and we could write a for loop and we could do a if entity equals this saved entity, then do this. But this is both slow and honestly kind of ugly. And at Bevy, we actually care about that. And the way that this works is Bevy's actually has very fast random access lookup for individual specific entities when keyed by their identifier. And this completely, once you figure out that this exists and this is a thing, this is the moment where Bevy starts to click. This is where you start to realize, oh, this is how I'm supposed to use this library, and it's not just all in order iteration. And so if you call query get or query get mute, you can access the data of specific entities in at one time. It's constant time regardless of how many entities there are. And so you get all of the benefits of a hyper-optimized vector for very fast iteration, and it also works like a hash map. And this is incredibly powerful. So something that comes up is you say, okay, I only care about processing this data when it's changed. So we have some system that will go and update and run and preserve some invariant, or maybe it will cache something, or maybe it will check for these changes, then propagate it out to somewhere else in the game. And it doesn't matter if we repeat this work, it would just do nothing, but that's wasteful and it's slow. And it would be really nice if there was some sort of like robust general mechanism for this, so then we don't have to like store, okay, here's the old copy of this data, here's the new data, and then we go and we check it, and like that's a lot of boilerplate, and it's really easy to screw up if you write it 100 times in a single game. And what Bevy does is every component, every resource, you can check if it's changed or not. And what we do is we have a timestamp mechanism where you say, here is the last time that this component changed. Here's the last time this system ran. How do these compare? And if the component has changed since the last time the system ran, then we go and we check and we say, hey, this data has changed, you may want to look at it. And it's really lovely when you combine this with existing ideas like query filters, where you can say, I want the data of component A, but only if the data of component B exists and has changed since the last time this system ran. And it becomes very, very smooth to write these really interesting, very gameplay relevant systems. So suppose we want to go and look over all of the entities and do exactly the same thing to each of them. In that case, we just want to do linear scans. This is perfect, this is easy, this is fast. But there's a lot of problems like collision detection where you can't do that. Like you will just you will run into quadratic performance with millions of entities, or you may have or worse. It would be really nice if you could integrate things like quad trees directly into the ECS, or have some blessed pattern for it at least. But wait, ECS is basically just a database, right? It's a specialized in-memory database with strange performance characteristics, but this is just a database. These are just database indexes. How could we go and expand this idea into a first-class feature? And so these are indexes. They may be spatial indexes, but they may be ordinary indexes. And you can write a naive solution for them really easy. You use some sort of acceleration data structure, whether it's a hash map or whether it's a quad tree, and you map the values and the entities together. And then you just store it in a resource, and then you just ask the resource, okay, I want all of the entities within this region of space, or I want the entity that corresponds to this tile. And it goes and it looks it up and it fetches it. And this is a shockingly effective solution. It could make your game dramatically faster. But the problem with this is that, well, synchronizing state and cache invalidation is actually really hard, and when it goes wrong, things go very wrong, because you say, oh, I want the entity for this tile, and it's actually the entity for its neighbor. Or you say, oh, give me all of the polygons within this region of space, and oh, that wasn't actually right, and then everything kind of explodes. And so something that I want to do in the future, and that the community wants to do, and I think is honestly an essential feature of a modern ECS, is first-class support for indexes, both spatial indexes and much more traditional database indexes that can rapidly accelerate these sort of common value-finding operations. So we're going to talk a little bit about the core underlying architecture of how ECSs work. So ECSs, they take your data, they transmute it into this horrible soup of bytes, and then they stick it as closely together as they possibly can, and then read the data with raw pointers. And this is great, except for the fact, and this data will be arranged into things called archetypes, where entities with the same components will be arranged close to each other because they're going to be operated on each other in similar ways. And this works really well, except for the fact that when you then want to go and move around this data, everything kind of has to get shuffled, and it becomes a very slow operation that breaks you out of the nice hot loop that you have. And in particular, if you want to shuffle all the data, you can't run anything else at the same time because, hey, I was busy using that. You're not allowed to go and change how that memory is laid out. So ECSs have this idea called commands. So commands are basically anything that you could do to the entire world, to all of the data that exists in your game. You can just turn into a command and say, hey, do this later. And they apply only at the next flush point. And in Bevy, we have the ability to control precisely when these flush points are scheduled arbitrarily. There's no artificial restrictions anymore, but then they also get evaluated at the end of the current schedule by default. Commands are a complex subject, and they're often very performance sensitive because you may have to go and spawn 10,000 entities for this frame, or you may want to go and despawn all of the effects from the bullet that you just shot despawning. And one of the big things that you can do to optimize this is to batch the commands together, because the core idea of ECS is similar work should be done together. And if you have each of these commands, we're sending them one at a time. You're going out to the level of the world. You're going down, drilling down to the data, and then you go back out, and then you go back in, and then you go back out, and you do that 10,000 times. It's much easier if you start at the level of the world. You go in, and then you do the 10,000 operations. Then you step back out. Way less overhead. But in order to do that, you need to have some notion of what each command is doing. So command batching is on our list of interesting, cool future work that will make ECS better. So this is another very simple but very useful primitive. So it's often really challenging to know exactly what you're going to do when something happens. You may want to, suppose you have a collision. It's what happens when two objects collide? Who knows? Anything could happen when two objects collide. And if you're a library author, there's no way to write that all within a single system because you need to expose something for other users to read. And the solution is pretty obvious. Just use events. And events are very powerful, and they're very easy to model inside of an ECS like Bevies that has resources. You just have a list of things that happened, and you stick it in the resource, and then people read it out. Bevies' default event type is a multi-producer, multi-consumer. It's really simple, and it's double buffered, so you can read events from both the previous and the last frame. Works honestly very well. And you can see kind of some of the example of the syntax over on the left. You have an event reader, you have an event writer. But ultimately under the hood, like these are just resources. This is just ECS. But thinking about these tools and these extensions, it really helps bring together an engine and turn it from a tool that you use to make things go fast to something that you could see yourself writing an entire game in, where you could see all of the logic you could possibly imagine fitting inside of this paradigm. And when that does, it's like when you can fit everything inside of a single unified architecture, your code becomes so much nicer. So let's talk about other things you might want to do. So a really common thing that you get is you have this beautiful system that say runs your physics, and you're like, I don't want to run my physics all of the time. I may want to, pause the game. Imagine that, a game where you could pause the physics. And so we need some sort of abstraction for turning systems on and turning them back off. And we could go and have a core game loop, and we could say if game paused, then skip this part. Otherwise run all these systems. But that's not how Bevy works. Bevy doesn't have a single game loop that you write. You add systems to a schedule, and then they get run for you. But we could also handle the special case this in each system. We could say at the start of each of our systems, we could say if the game is paused, then return. But that's really easy to screw up. Like if you do this 10,000 times, then you have some systems that are running when the game is paused and some that aren't. It's going to suck. So there's a simple abstraction and a slightly more sophisticated one here. So the first one is run conditions. So before each system is run, before a task is dispatched for it and it gets run, we check some data from the world, and if that function that we call on the world returns false, the system just doesn't run. If it returns true, the system does run. And these are just ordinary functions that can access arbitrary data from the world in a read-only way because Rust is cool. And it goes and it says, and you can use these and combine them to create these really complex behaviors in a way that saves you substantial performance. But when working with run conditions, there's actually another abstraction that's often quite powerful, where you have a state, your game as something of a state machine, where you have things that you want to do when you go into that state, there are things that you want to do when you come out of that state, and there are things that you want to do only when you're in that state. And so we have a fairly lightweight abstraction that does exactly that. You'll go and say when you enter this state, run this system. When you leave this state, run this system for set up and clean and tear down. And then you have when I'm in this state, when I'm in the game playing, run all of these game logic systems. And this sort of flexibility and simplicity works really well. And you can do incredibly complex and powerful things with Bevy scheduling. You can create entire schedules of your own, and then take a system that mutates the entire world and run arbitrary game logic using branching and for loops and random numbers to generate what game logic you want, and it just works because it's all just Rust code. And something we want to support in the future is dynamic schedule modification, where you say, at runtime, I want to control which of these systems, what systems are in my game. This is controversial because there is we do a lot of work to initialize schedules and to ensure that they're valid. So this is not a tool you want to reach for all of the time. That's what run conditions are for. But if you want to do things like support game mods without forcing a reload of your game, or you really need to squeeze out the last bit of performance between levels, you can just do this. And then your systems, they aren't checked ever because they're just removed from the schedule. So this is talking about a very new feature that I helped write and was going to be shipped in the next Bevy release. And the core idea here is you have, so systems in ECS, they run every frame, and they're basically just polling. They say, hey, is there any work for me to do? Is there any work for me to do? Is there any work for me to do? But that's not how you want to write all of your control flow. Sometimes you want it to say, if this thing happens, then do this other thing, right? You don't want to be have 10,000 systems to be like, hey, did this button get clicked? Are you sure this button isn't clicked yet? And each of them will do different things, and then you have 10,000 pollers, one for each of your buttons. Like this is slow, this is complicated, this is kludgy. So if you have a game like Hearthstone, or you have something like UI, you want to respond dynamically based on the game state or player input. And you know, if it's a game like Hearthstone, or if it's a game like user input, it's just use scripting. Like just use scripting, send events, and read it in. But you don't have to use scripting. What if you could just write this all in Rust? What if you could write this all in ECS? And so this is the work that we're going to be shipping called one-shot systems, where they're systems that are run exactly once on demand. And this, of course, is completely heretical. It's controversial. That's not how systems works. That's not how ECS works. They go and they run and they check for work. But performance isn't always what you need. Sometimes you want this flexible, powerful, expressive logic. And if you go and you hook it into the ECS, you can write these things that work exactly like any other system, and you can just run them. You can say, hey, when this button is clicked, do this thing. Oh yeah, oh hey, we have callbacks. Like they're not incredibly slow, but they're not incredibly fast. But that's good enough for these complex one-off events. And I'm really, really excited to see what the community can do with them and what they can build in the future. So there's a couple more features here. We're getting into the more experimental, more advanced, more future work. So something that happens is sometimes if everything is ECS, you'll get things that probably shouldn't be interacted with by default, like your window. If your game window is in fact an entity, maybe don't despawn it recklessly. Or maybe you have something like this object is 5 screens away from the player. Don't try to simulate it. We want it to be sleeping. And so we could go and we could add a custom disabled component to our systems, which we want to then go and filter on all of those relevant systems to say without disabled. But that sucks. Remember having to write without disabled everywhere on all of your systems, otherwise you get these horrible, strange bugs, is bad. And fundamentally, if the engine systems don't know about this custom disabled component that you have, the library of plugins that you don't know about the disabled component you have. So how do we actually solve this use case for users? So what I propose is that there should be a special disabled marker component, and by default, queries exclude entities with that component. So you take the logic and ordinary logic and you flip it on its head because you want the default behavior to be correct, and then this solves all of those ecosystem compatibility problems. But at the same time, if you say with disabled, it'll show up for you, right? And then you can go and you can inspect it, you can re-enable it, you can go do strange things by running game logic on disabled entities. And this isn't a new idea, but it's very powerful, and I think it's honestly a important and valuable part of what makes an ECS actually useful for users. Existing work also uses this for prefab entities, so entities that are already like made up, and you can just quickly copy them and say, I want to spawn another another goblin over here, and another make another tower placed right there. And so we still need to implement this in Bevy, but this is one or two pull requests. This is hey, if this is cool, you could do it. And ultimately, I think that users should be able to make their own components that work this way. They can just take the component trait and we can just add an associated type that says, is this opt-in or opt-out? And then they can have their own components that work opt-out. And by doing so, it'll work with all of the other stuff in the ecosystem automatically. And so we get to the final and most complicated feature. So ECS is really good for storing objects that are flat. But what happens if you need to go and reference other things in those entities? So if you're clever, you might be like, oh, that's easy. We'll just make a component that stores an entity inside of it, and then we can use that basically as a pointer, but like as a keyed pointer to things. But what happens if that entity is despawned? What happens if we want to make sure that all of our relations that are defined this way form an acyclic graph, or form a tree, or like have this other very important consideration? Do we go and validate it every time and then panic if it breaks, or how do we do this? And fundamentally, when you have these graphs, you want to walk around on graphs. You want to get the parent of my parent, or you want to go and say, for each of my descendants, my recursive descendants, go and do this operation. And this sucks, and it's painful, and there's no way to abstract over them between different relationships of the same, different relationships that mean different things. We could have a single parent component, which is what we currently do. We have parent and child. But if you want that to mean different things, it becomes very challenging to implement efficiently. And so this brings us to I think, the frontier of ECS systems. This is something that Flex by Sander Martens has really pioneered. The idea that we could take this idea of a component that points to another entity and make this a first-class feature of the ECS. And we could do this in a way that's ergonomic, in a way that's fast, in a way that's robust, where you could have mechanisms for, I want to get my parent, or I want to get my parent's parent, or I want to look at things, I want to do a depth first search or a breadth first search. Could be first-class built-in algorithms to the ECS, and they could be very, very fast. And this is something that we've been exploring actively within the ECS development community, and this is something I'm looking forward to the next talk that I give about ECS to be about relations and why they rock. But because Bevy is so incredibly modular and so incredibly hackable, somebody took the public interface of Bevy and they added relations to it, which is completely ridiculous. And I'm looking forward to learning from that, and I'm looking forward to extending and optimizing them, because I think that ECS can be used for entire games, and I think that this is the final missing piece. So that's all I have for you today, and I want to go and I want to say that the people who are like, you're crazy, you can't write a game entirely in ECS, it's just a performance tool. Those people, they were right. But I don't want them to be right anymore. if we go and we take our engine and we unify it all into a very nice ECS framework, you get performance for free without having to think about how to make your code fast. You get these beautiful and intuitive emergent mechanics. You get a single stack for gameplay and engine code that all looks the same and is very easy to read and modify. You have you can make awesome intercompatible ecosystems, and you have this incredible developer experience. So that's all I have for you today, and thank you so much for listening. If you have questions or problems with ECS, feel free to get in touch, and I'd love to make this better for you.
谢谢那个 Alice 给大家的精彩的分享啊，看大家有什么问题。
I have something about a schedule system. Yeah, I remember those cars. The first thing is, the first branch is V1. Version 1 is focus first on the region. Yeah, the regions branch, and now it has has a version 3 branch. So what's the intention about the evolution of the schedule system?
Yeah, so Bevy's schedule system has evolved a lot over time, and this was something that I've been deeply involved with. I led the rewrite of the most recent rewrite of our schedule. So the way that schedules work in Bevy is you have a schedule, which is a list of systems, and then you add systems to it, and you say, how do these run? And initially, this was pretty simple. This was built off of Hex, which was an existing Rust ECS, and this was fantastic for prototyping. But it didn't give us quite the control and customizability that we wanted, and that was the rewrite to Schedule V2. It was called, but as we started to add features and as we started to develop it and to refine it to the users, we got ourselves in a great deal of mess. We had been adding features one at a time and not really thinking about how they fit into everything. We hadn't been explaining it properly. We had redundant abstractions. We had both schedules and stages, which were fundamentally the same thing. We had booleans with 4 values, where rather than saying should the system run or not, you got a boolean that was yes it should run, no it should run, yes it should run but we should loop, and no it should run and we should loop, and then it's okay. How do you compose these? There was all sorts of dumb things where you couldn't compose things like, oh, I want to run my system on a fixed time step with states. There was all sorts of horrible tech debt that have been caused by adding these features one at a time without really thinking through the interaction or having a central architecture. And so the Schedule V3 architecture was an attempt to say, okay, what are the things users actually want to do and that actually care about, and how do we design a simple and elegant model for how to do that? And the answer, ultimately, the answer was, it's all just schedules, and you just call world.run schedule when you want complex logic.
Furthermore, what's the purpose of canceling the stage system from about the version 3?
Yeah, so we wanted to remove stages in version 3 because fundamentally they were an abstraction that was very, very, very similar to the schedule abstraction, where it's a container that stores a bunch of different systems. And so by combining those into a single abstraction, things became much simpler.
Thank you.
看看还有什么问题。
Thanks for sharing. Does Bevy have any plans related to a visual editor, similar to Unreal or Unity? Yeah.
Yep. So Bevy is working towards visual editors, specifically targeted at things like level editing, things like debugging, rather than things like Unity's blueprints, where you like blueprints, where you go and you write code, or things that kind of work like code in the editor. But for artists, for people making levels, you need to have that interaction and that visualization to make this feasible in order to see what you're doing. You can't just write it all in a file and then say, okay, now we're gonna run the game, and then we're gonna go back, and then now we're gonna run the game, and then we're gonna go back. Like that's awful. So yes, Bevy is working towards an editor there, and that's one of the biggest goals of the development at the moment.
还有问题吗？好。
你好，感谢你的分享。我想一下，就是后置我们这个 ECS Code 会和 ChatGPT 这样的一个结合吗？就比如说，通过 ChatGPT 可以生成这种组件和代码。谢谢。
So there's kind of two ways to interpret this question. So one choice is, can ChatGPT and other large language models write Bevy code? And the answer is, yeah, reasonably well, better than you might expect. I use Copilot sometimes, which is Microsoft's version, and it's very, very good at predicting exactly how to make well-structured systems, functioning systems, because it's very well-structured and because there's not a lot of complex plumbing that you need to do. But if you want to use ChatGPT in your game, yeah, it's absolutely possible. I've seen people experimenting with AI integration in Bevy and in your app. It's just an API call. You just call it to the network, or you call it to a local copy of a language model, and you do it. The big challenge with doing so is, how do you do so in a way that makes your game more fun? How do you do this in a game that makes your game more interesting? How do you do this in a way that makes people want to play your game? It's very easy to, when working with AI, to say, oh, well, we added AI to our game, and then people give you money, but those people are investors. They're not players who want this because it's more fun. So that's something I've thought a lot about. I spent a couple months working at a startup adding AI to Bevy and to Bevy games. So if you want to talk more, I'd be happy to.
Thanks for the presentation and question. And in terms of like a 3D engine with like Unity or Unreal, what are some of the advantages? And now similar question is for like 2D, like Google's Scale. Like do you have like some comparison, information?
Yeah.
In terms of the performance.
Yeah, and so in terms of performance, our performance is currently okay. It's not as good as it should be. We were seeing there was somebody doing recent performance tests in VR, and they were getting numbers that were somewhere around the level of like Unity or Godot, but our rendering is not as optimized as it should be. It's still in the experimental phase, and we're often missing a lot of critical rendering features, even if it is easy to write them yourself. I have a talk coming up on the 26th about, is Bevy ready for your commercial games, and is this and what are the advantages and disadvantages of it? And I think you'll really like that one.
All right, thank you.
他刚刚提到的 26那个是 KubeCon， 就是说星期二在 KubeCon 的那个会中会里面，他会讲一下这个 Bevy Engine 在 commercial 的 potential 的可能性我们时间也差不多了我觉得现在 Bevy Engine 确实是一个非常好的一个开源的引擎，特别是现在 Unreal 和 Unity 的 license 的问题，这个而且 Byway 会是永远开源，很大机会。在我Thank you Alice，在我introduce 下一个 speaker 的时候呢，我们组织方我们来照一个合影，照一个我们这个 track 的一个全家福啊，你们到we need to take a picture for 大家都上到台上来，照一张合影，然后我们就下一个 topic， 好吧？我们到台上来，跟我们的 we want to take a whole picture for the group.
Okay, sure.
Okay, let's take a picture. Take a picture, yeah, everybody. 所有人都到台上来，我们照一个全家福。谢谢大家啊，谢谢大家的合作。我们下一个 speaker 呢是吴小毛先生，他是理界科技创始人兼首席执行官。他今天给大家分享的题目是在游戏引擎在跨领域，在跨领域应用中的机遇和挑战。欢迎，谢谢。
好，大家上午好。那个刚才 Alice 的报告非常精彩，就是以 Rust 为基础的这种游戏引擎，我也一直在思考，就是下一代的游戏的引擎的构架，它是不是会逐步的 Rust 化，然后会不会像 Sebastian 这个物理引擎那样，做成一个更加端云的构架啊？这一直我在思考的问题。然后回到这个开发者现场，非常的熟悉，因为我原来就是程序员出身的，所以我路过我们公司程序员屏幕的时候，非常羡慕他们，因为我每天其实没有多少时间编程，但是编程是一件让人非常幸福的事情，所以我的理想就是我的公司如果能够运行到我可以每一周有一天编程，那应该它是运行的比较成功的，那我为什么会选择这个跨领域的应用呢？因为游戏引擎在游戏领域的应用大家比较熟悉， 在非游戏领域的应用相对来说探索的比较少，而且我在游戏引擎跨非游戏的这个领域里面已经工作差不多10几年了，所以就把一些我的工作的一些体会，每个领域它的问题给大家介绍一下。然后非游戏领域其实是游戏市场的3倍左右，所以只是它比较分散，所以这个领域我希望开发者们和各位专家能够多多的关注，然后花更多的时间去研究它，因为这些领域更需要我们的游戏技术。然后我原来不是学计算机的，后来对编程非常有感兴趣之后，我就自学计算机，然后进入上海交通大学获得了博士学位。后来去法国的国家计算机与自动化研究院 INRIA， 然后做了2年的博士后之后 ，Crytek 的 CryEngine 这种非常酷炫的物理效果和开放世界的游戏，深深的吸引了我。然后我当时应该是研发部唯一的中国籍的工程师，然后不光做了《孤岛危机 Crisis 2》、《孤岛危机2》，还有《罗马之子》，还有这个后来我也开始做这个，把这些技术用在好莱坞的影视作品里面。然后我也在 Autodesk 工作过。我们公司的产品也是一个引擎啊，也是一个引擎。那我们引擎名字叫 CreateGene， 我们有2个版本，左边的对标的是 Unreal 虚幻引擎，右边对标的是 Unity。当然，我们每个引擎它跟 Unreal 和 Unity 在现时代的游戏方面还没有100% ready， 但是已经基本上达到70%、80%的这个 ready 的状态。所以我今天要讲的是这些引擎先用在非游戏领域的这个应用，然后反过来我们会再回归到游戏的领域。这是我们对标 Unreal 的那个，就是更加偏云端，然后更加偏专业版本的这个引擎。那里面我们基本上的这些 entity 的操作，还有光照的操作，还有这些 copy paste， 纹理的设置，还有场景的搭建，这些我们基本上是非常完善的。然后我们整个 UI 是基于 Avalonia 一个开源的 UI， 就是我们这个引擎把那个 Avalonia 的整个的吹得更加成熟，而且打开了差异化，有点像 Adobe 的这个界面 ，Adobe 设计的3D 引擎界面。比如说远处的这些雾的效果，是我们兼容了很多影视的这些特效，还有这些物体的搭建也非常方便，还有 Material Editor， 以及这些阴影的 Shadow， 还有我们跟 Crytek 一样是 Real Time All the Time， 我们不做 Baking。OK， 这是我们引擎的一个 Editor 一个状态，然后这是 Real Time 渲染出来的一张图。那除了这是我们引擎的3D 编辑的一个状态。然后其实我们的 timeline 也做得非常好，就是在 CryEngine 的基础上，我们做的更加方便使用，更加的简洁，更加针对 real time 的 visual effects， 还有 film editing， 还有这种商业的广告片。然后我们的这些像毛发的渲染，应该会略比 Unreal 会更加真实和更加就是贴近用户一点啊。像这些真实的毛发的渲染。以及我们对 Alembic 像 Film 的一些标准格式的支持，也会支持得更好。像我们导入 Alembic 还能编辑 Alembic， 而且是非常高效的。然后也支持 FBX 和其他格式的导入。这是我们的一头狮子，这是那个叫轨道 Ghost Blade 里面的一个 character。然后我们还有一大特色是，因为我做好莱坞的影视做了很多年，所以我们把很多影视界的标准引入过来，像这种 ACES 的光照的系统，还有 Open Color I/O 这种颜色校正的系统，这些对引擎做 film 是非常重要的。然后这是我们的专业的版本，还有一个版本是更加偏 mobile 的，这是我们和很多的中国的企业合作时候使用的比例比较大的一个系统。它是一个更加 lightweighted 这种引擎，然后它主打的是低功耗，还有跨终端、跨端云的这种结构。像这是我们是一个游戏的场景，所以它比其他的游戏引擎，就是商业引擎可能会更加容易学习一点。那我们会进一步通过 AI 的工具和极大的降低它的门槛，让更多人能够使用这款工具。那我们也支持这个粒子特效，还有场景的编辑。另外，我们可以一键 export 你到不同的这个 platform， 像手机 还有 PC、Pad， 还有 VR 和 AR 设备，以及 MR 的设备，我们都支持。这个在我们中国市场应用非常广泛，然后我们也支持移动端的全局光照，我们对移动端硬件花了很多时间去优化，然后去跟踪最新的移动端的这个性能，这个硬件的充分发挥引擎的性能，然后也支持面光源，所以我们是在因为移动端的对功耗要求非常严，所以我们会在功耗端会有非常优秀的表现。在某些场景，我们甚至也优于 Godot 和其他的一些商业的或者开源的解决方案。我们也支持 Reflection Probe， 所以这些要运行在像我们的车机系统，还有我们的手机上面，而且作为一个日常应用，如果要打开这个应用，其实要求是非常高的。我们也支持实时的布料。还有个特点是我们有端云的构架，就是因为端的算力是非常弱的，所以我们应该用云去增强端。而我们现在整个市面的做法是直接抛弃端的算力，想直接放到云上，我觉得这是一种错误的设计。我们的计算，我坚定认为是从端到编到云的，不是说从端直接跳到云。所以我们这套构架，刚才您看到的就是说，当我们端的算力不够的时候，我们会用云或者编的算力来增强我们本地的算力，使得它达到以前工作站才能达到渲染的效果。然后我们也支持Blend Shape、Dynamic Bone， 还有脸部的追踪，还有身体的追踪系统，所以功能已经比较完备了。当然也支持 AR 和 VR 和 XR 的设备。好，那其实我以前是做游戏的，就是我进 Crytek 的时候是被游戏引擎所吸引，所以我是被孤岛危机，就是他当时用枪一射击那个树，然后叽嘎叽嘎那个树往地上一倒，对吧？木屑还不停地掉出来。就是我在 Inria 的时候就觉得这东西，我们整个 Inria 的 graphics 小组都非常觉得这个 Crytek 这个公司非常厉害，所以我觉得我要去工业界做这种非常酷炫的这种 rendering。好，然后在这个过程中，我们发现其实游戏引擎的品质已经接近于好莱坞的特效了。我们来看一下。好，大家知道我们影视的技术和游戏的技术其实几乎同时开始在这个行业开始发展，但是其实影视的技术越来越落后于游戏的技术了。那以前两个行业是相互看不起的，就游戏行业觉得影视太慢，影视行业觉得游戏的品质很 low 逼，所以当时整个公司只有我跟 CEO 还有少数的不超过5个人，觉得这个是可以干的。然后经过3年的努力，CEO 给了我足够的资源，我们通过3年的努力，让一个游戏引擎变成可以渲染好莱坞电影的这个引擎。然后这个其实从来没有公布过，因为今天也没有在线直播，刚才问过了，所以我会有一些比较私密的一些话题，但大家不要去发社交朋友圈啊。比如说我们下面的《移动迷宫2》里面有80个镜头，就大家看到《移动迷宫2》是有3屏版本。然后那个版本里面有80个镜头是用我开发了这个引擎做的，然后这段历史从来没有公开过。我们来看一下，这个颠覆大家对游戏引擎的这个看法。我们来看一下。等一下。好，我们先看这一段，好吧？我跳过这一段啊，我们来先看这一段。Sorry。就当时让导演们还有观众都觉得非常惊讶，而且它成本基本上可以降25%最少，然后开发周期可以加快1倍。好，然后这是第一个领域啊，当时就是游戏引擎当时它的特效已经让365家，我当时数过，365家好莱坞的 Visual Effects Studio 来找 Crytek 说，你们能不能把这个引擎做成一个可以用来做影视的引擎？所以经过3年的开发，我觉得基本达到了经过我们的辅导、我们的培训可以去用的这么一种状态。 但是发现其实离能够给所有的人、给所有的 studio 都能用还是有距离的。所以我后面创业来做我们GridVolt 历届科技这家公司，就是想用一个新的构架来服务于这些，同时服务于游戏和非游戏的市场。好，这是第一个。那当时其实除了影视特效之外，还有一个叫数字战场，就是用来做军方的模拟。这是美军啊，这是美军用我们 CryEngine 当时做3军联合演习。这套系统里面的这运动捕捉的模块，也是我和一个叫 Michelle 的女孩子一起开发的。我们来看一下。好，不好意思。这个我们叫 Serious Gaming， 就是游戏的技术能够真正用来我们的像国防模拟演练、消防演练等等。这是陆军的夜视镜模式，其实跟游戏已经非常像，只是它要把很多士兵身上的数据要直接 transfer real time 的 link 到游戏里面。这是空军的飞机。这是海军，所以这种演练能够大大降低实际演练的成本。这也是我们国家在大力发展的这个技术啊。然后它同时大概能够当时能支持10到20个士兵，就同时接进去。如果你要接更多，要用好几个场地。那现在我觉得它支持的范围也越来越广。好，所以我们前面讲到了2个领域啊。然后就是游戏引擎在做好莱坞的影视特效的时候，以及刚才提到的这种实时的士兵演练之外，其实当时我们中国有个叫玄机科技的公司啊，它可能是现在在全球来说实现动漫用游戏引擎渲染的一家公司，而且做得非常好。他们有几百号员工，天天在用这个游戏引擎来制作他们的动漫番剧。我们来看一下，就是说用 Game Engine 做出来的这种我们叫 animation 这种卡通 animation 3D 的，它是可以降1半的成本，而且效率可以提高8倍。就以前大家看《秦时明月》可能要2个月更新1集，后来我们做到了1周1集。我们来看一下，这是《斗罗大陆》。然后这是新情变，我们叫一镜到底，是中间不能切素材，整个素材要实时的 stream 到引擎。就大家看到市面上有很多，比如说用游戏引擎也开始来做这种特效，但是真正能掌握这套流程的公司很少。就是如果没有 Epic Games 或者说一些像我们公司这种专业团队去指导的话，其实是很难实现高品质的渲染。因为游戏的东西跟影视特效的这个匹配度其实有很多差异化。比如说它的资产非常的大，比如说主角脸上一张纹理就好几个 GB， 可能就是我们一个游戏的体量。这么大的素材进引擎通常会崩溃。还有导演是非常喜欢确定性的东西，但是我们游戏是不喜欢确定性的东西，反而就不好玩。等等，还有数据的导入导出，还有用户的使用习惯，都是巨大的问题。然后接下来这个是一个叫 GOSIM 的，全球大概有几百万上千万的粉丝，大家可以 YouTube 上面去看。然后我们历届科技就是自己创意设计，和玄机科技一起来联合的去指导的这个作品，然后渲染的也是用我们历届的 GridGen 引擎，100%实时渲染的。我们来看一下。 cosplay， 它是个漫画作品，大家可以去网上搜索一下，深得粉丝们的喜欢。所以这个引擎我们做了7年，而且18个国家的人才，因为我们在德国有一支团队，一起联合攻坚才实现了这个突破啊。然后游戏引擎也能用在像这种建筑设计和招商。我们和 K11的很多楼，他们以前在修改方案的时候，就发现告诉供应商一个修改方案可能要经过几天到几星期的时间才得到一个更新的版本。所以有了游戏技术之后，它可以直接在现场就可以修改。我们当时就拿着电脑，就到他们 K11的招商的现场。那他们招商部门要修改任何的内容，我们现场去修改，修改好就直接导出。所以他们非常喜欢这种非常 real time 的解决方案。所以里面的细节在装修完之前就可以呈现，然后也可以供客户去选择他的租赁的位置。但是建筑领域的渲染和我们游戏引擎有一些区别，大家可以看到它的光是非常明亮的，而且非常讲究那种实际的光照的渲染，就不允许实现那个偏差。但是我们游戏里面是要艺术感的。视觉的冲击力是优先。然后因为这个疫情的原因，也是因为我们效率的提升的原因，其实我们这种像发布会、演讲会，它会越来越被虚拟现实化。所以以后的演讲，我觉得可能大家像在座的这位外国的国外的这些专家们，他可能就可以在自己的国家拿个这个绿幕，甚至绿幕都不需要了，有了 AI 之后。就可以跟我们一起来参与到我们现场这种互动和会议里面。这是我们和造就合作的一个直播系统，它其实那个人是在一个虚拟直播间，然后整个的舞台包括 PPT 都是游戏引擎来进行渲染的。
Have shaped London's past and will shape its future. London's reinvention starts above our heads. Many of our lampposts are over 100 years old, like this one, but it's also part of our future. London is now planning to fit out lampposts as 5G access
Game
points,
Engine 其实
bringing
对于这种
super
绿
fast
幕的
data all
高
over
质量的
the
绿幕的
city.
集成，还
From
有整
above
个的
our heads to
pipeline，
below our feet,
还有以及素
London
材
has
的
long
缺失
been
是
a
目前主要
global
的一个问题。
pioneer in urban infrastructure.
另外，游戏引擎特别是在中国，这一套就是叫 Digital Twin 的这套系统啊，得到了应该是市场最大的应用。大家看到中国的整个的数字孪生的市场，应该在全球排第1了，就包括政务管理、工厂的管理等等混合在一起。所以我们来看一下，这是我们和联通合作的瑞金医院的一个指挥中心。所以它其实就是给管理者一个游戏工具来管理它的整个医院，它也是个游戏，但是游戏是用来管理而不是用来娱乐。所以这里你看它有3个房子，然后左边是一些比如说服务的人数啊，还有就医体验的一些数据，然后右边有监控录像，然后上面有资产管理。所以你通过这种游戏的方式，可以非常快速的来获得你需要访问的数据。然后也可以直接进入任何的楼房，然后你进入某个楼房之后呢，其实也可以切开任何一层，看到里面真实的里面的数据，所以比你去寻找很多监控录像或者说一大堆的2维数据来去搜索的话，会方便很多。这是打开监控，然后进入一个比如说消化肿瘤大楼，然后里面各个病房楼都可以直接选择。然后选择之后，应该就可以选择一个楼层。选择楼层之后，你可以再进去切开，所以你可以看到病床，还有护士和患者的状态，以及它的设备如果坏了，你怎么去修？它有一个手机端的导航把你导过去。所以它是个大屏和手机互动的这么一种应用。所以这种应用不光是可以在医院里面，它以后会到我们的学校、到我们的办公室、到我们的园区，直到整个的城市和整个的国家和整个的地球，我们才能真正实现数字孪生和混合现实的体验。所以这个是一个基础性的工作，非常重要。 而且现在做这个应用的人呢，就这些企业，其实他们都要去维护这些商业引擎，成本非常高，所以整个行业也没有出现一个标准化的应用，能够直接拿来就不用学游戏引擎就能够使用来做这些3D 数字孪生这样的工具并没有出现。下面一个我们做的工作就是大家参观我们历届前办公室和现在办公室，正好我们在这个办公室做了我们的混合现实体验。我们来看一下，这是用我们历届的 GRID 引擎呢来这个应该是和华为合作的这个啊。我们来看一下，就是我们想把办公室做成一个 XR 的迭代体验和设计中心，所以它包含了各种交互。这是我们的同事他扫描了这个之后，那我们用华为的定位技术，就可以把空间扫描，然后它的这些白膜和定位都可以非常精准的设计出来。这是我们用手机展示的，但是也可以用 XR 的眼镜来看。这是我们历届小机器人小丽，这个 logo 也是虚拟的。你看我们引擎那个半透明其实做得非常好，叫 OIT 啊 ，Order Independent Transparency。所以这个 logo 也能随时换，而不是说你装修之后就不能换，而且颜色也可以随时换。然后员工到了之后，可以在左边签到，就你用手在屏幕上就可以把自己名字签上，就看到谁来了，所以它是一个虚拟的一个签到板。然后那个圣诞树和下面的礼物也是虚拟的。然后我们希望每一个员工都有一只宠物，所以它会一直陪着你在你的 office， 让办公室不再冰冷，是吧？让办公室温暖起来是我们非常非常重视的一个点。所以签好到之后，就可以往办公区走。然后这个是一条动线，就是引导你进去参观。然后我的宠物，对吧？毛哥的宠物就跳上来了，说我饿了，是吧？要给我个骨头吃吧。那我就可以去喂它。它是一个多人互动的啊，就是很多员工可以拿着这个手机一起来玩这个游戏。这是第3视角，就是我用手机是看到的是这种状态。好，大家知道我们的脊椎和腰通常不太好，程序员的脊椎也不太好，是吧？我的脊椎也是有点问题的。那我们可以投篮，是吧？就举高，一起玩一个多人互动的篮球游戏。也可以进行这个比赛，然后也可以扔飞镖。这2个活动呢，大家都非常喜欢。然后也可以用来做客户的方案讲解，就是我们数字孪生类的项目，就可以在这种方式下给大家讲，哎，它是一个什么东西，我能做哪些功能，这样客户就有一个非常直观的感受，而不是用一个2D 的视频来给他展示，而且这个是可以互动的。好，这个是对客户的这个方案的吸引力。同时呢，我们也这个引擎也能够支持一些物理，我们也支持物理计算。我们集成了物理引擎，所以打开我们后面一个美女是吧？这是海星烟。然后如果办公室是非常 boring， 我们就可以把这个顶打开，这样我们可以看到一个更加漂亮的世界，缓解我们办公的压力。而且我们有集成了 UGC 的功能，就是你画一个圈就可以出一个气球，选一个颜色。然后它就可以飞到天上去。所以我们非常希望游戏引擎能够交给越来越多的用户所使用，而不只是专业的人员所使用。也可以切成这种浩瀚的星空。这是我们在杨浦区的办公室。然后现在我们搬到了徐汇的潮河津，就是有了一个升级版本。我们是希望把我们潮河津的办公室变成下一代的 XR 的设计、体验和测试中心。我们来看一下，这是我们的一个，这是我们历届的一个会议室啊。那会议室里面，我们把它做成了一个终端体验店，就是手机体验店。我们会持续的迭代这个版本。
小丽 AI 机器人。
然后这个 AI 机器人是集成了文心一言，百度的文心一言。
增强现实是一种将虚拟信息与现实世界相结合的技术。
传送门 AR 汽车体验。
那也可以进行
汽车
车的体验和
内饰、
设计。
车机展示。
就你可以在我们办公室就可以来设计和体验你的汽车，或者装配你的汽车。
汽车虚拟体验。
比如切换它的颜色。
植被生长。
然后你走进去的时候，那个植物是跟着生长。这个，哎，这些小
保
猫
龄球
你是可以领养的。
游戏。
也可以打保龄球，是吧？
宠物交互跟随。
那我们宠物的数量在迅速增加，所以以后每个客户也能领养一只宠物，而且它是在云端不停地
历届游戏
不停地生长。
介绍。
这是我们3年以后想做的游戏的一个 concept design， 就是一个女孩发现这个世界是被模拟的，然后在她绝望的时候，就有历届我们创造世界
多人篮球游戏
进入这个游戏。也可以玩多人互动的篮球游戏，这个大家都很喜欢，而且以前太难了，没有人可以打中。现在我们有 hack 版本，就领导一来，只要摁一下就能中，是吧？领导都很开心。以前我们很尴尬，说，但是你往这里再毛一点，是吧？半天都中不了。我说你们一定要有一个叫我们游戏里面叫 God 模式，是吧 ？God model 等于1，然后领导们都能中。好，前面是我们的一些工作啊，因为我基本上都以视频方式来展示。那我们可以看到，其实我们历届是特意避开了游戏赛道的。就是我其实真正是做游戏出身，我发现下一代的游戏引擎的构架一定要从非游戏开始做，不能是从现在的游戏去做。因为非游戏它会推导出一套新的端云，更加让更多的人使用并降低门槛的这么一种这个机会啊。我们叫 serious gaming 游戏。那么严肃游戏行业的痛点，我们说游戏本身，它也面临比如说云端多 GPU 的方案不成熟，它很难利用手机端的 CPU 和 GPU 的算力，然后没有端云的方案。那智慧城市呢，就是它是不能等待，比如说我们游戏一个关卡一个关卡过的，它必须要整个的国家或者城市最起码能够无缝的去切入，然后它数据通常也太密，就是我们游戏引擎根本没法承载，都要经过简化。能不能有更好的简化的算法，来降低这个大家的重复制造数据的这个难度？以及其实政府对引擎是有自主可控要求的，所以也给我们在座创造了机会。还有影视动漫广告是它的速度太慢，它是游戏引擎的1/5，所以这个是非常惊人的。所以这个我觉得对行业的生产力的提高非常重要。然后它的成本也非常高，所以在这个行业的这些企业其实都不怎么赚钱，生活都非常艰难，包括好莱坞的公司啊，每一个画面的背后都是血泪啊。然后 AR 就是功耗高，然后没有端云的解决方案，这套交互其实也要用新的引擎来进行支持。还有建筑家装，其实它的渲染的那个光照啊，就是跟我们游戏引擎有较大的差别。然后车载系统。大家可能注意到，我们最近获得比亚迪的投资，就是我们在3D Graphics Engine 在车这个赛道，其实一个非常重要的应用点，大家也非常关注啊，就是智能驾驶舱，里面的3D 的交互，它的语音的交互，其实车可能是 MR 的一个非常好的实际性的试验场景，因为语音、手势还有多屏的交互，还有以后车的玻璃变成一个显示器之后，它其实就是个移动的 MR 的设备。还有教育和模拟和演练，我刚刚大概说了一下，就是他们其实教育行业是非常需要门槛极低的3D 工具，就是没有经过学习老师和学生就能创建内容，非常重要，而且有海量数据库的支撑。那我刚才说到，我们是从非游戏是吧 ，non-gaming， 再向 Metaverse 进军，而现在的引擎是从游戏再到非游戏，所以我觉得我更看好的是从非游戏出发，再进军 Metaverse， 而且基本上整个赛道，我觉得这个机会是最大的，所以我们历届做2个引擎往这边走，就是这个思路。然后我们整个的第4次工业革命是我们目前整个人类正在经历的。大家提元宇宙提的太多，然后老师会问元宇宙是不是太虚了？元宇宙是被我们玩虚了，但是第4次工业革命不会虚。元宇宙是第4次工业革命的结果。大家如果聊太多的元宇宙，而不注重去为第4次工业革命努力的话，我觉得元宇宙实现就遥遥无期。那我们会发现，第4次工业革命的特点是什么呢？我觉得是数字智能， 游戏化和人人参与。所以我们的游戏技术一定会被快速的扩展到非游戏的领域。以前，游戏技术和图形技术没什么存在感，都是什么视觉、什么 AI 是吧？现在 AI 把一切都盖下去了，盖完之后大家发现好像也没什么爆款的应用，好像行业也推不动。我觉得核心是我们要去理解第四次工业里面的框架是什么，它是融合这些技术 ，AI 只是一个工具。我们如果不把这些技术连接起来，去把各个行业游戏和非游戏打通，去做更低的门槛，我觉得永远不会有突破。当然，主要是依赖于设备，是吧？所以下一代的游戏技术是接下来非常大的一个机会，它甚至会成为3D 的 OS、3D 的操作系统。所以在座的各位，如果在为游戏服务的话，应该我觉得是一个巨大的机会。接下来3年是整个 OS 定型的3年，核心原因是苹果今年推出第1代，明年第2代，2026、2027推出第3代。我觉得基本上 OS 就定型了，所以我们的机会在接下来的3年。那第4次工业革命的核心其实是游戏，游戏会成为主角，所以我觉得为游戏工作的工作者会非常的幸运。然后我们会从实时游戏开始去把，比如说3D 的管理、娱乐、社交、会议、创作、办公和小程序，在这里面我最看好的是管理和沟通。就是大家都会想爆款应用在哪里？我觉得爆款应用可能就是我们代替我们出差的这种沟通类的应用，以及我们的3D 的管理和下一代的游戏。下一代的游戏已经不再是一个纯粹的游戏 APP， 它是会打通你的衣食住行和工作的。另外就是人人参与内容的创作，不再是专业人员来为这个创建内容。所以我们看到现在的都是2D 领域内的标杆性的应用，接下来会有一个3D 的爆款应用，把所有这种都会颠覆一遍。而它的转换的支点就是我们的设备，比如说车，比如说 XR 的设备，还有手机，由于 XR 设备和车的这些新的交互，导致被反推的这么一种交互，会引领整个的变革。那我这里非常强调新能源的车，因为车是移动的 MR 节点，然后苹果的设备的爆发会引领整个全球的发展。所以今年苹果推出 Vision Pro 之后，其实各个厂家对这个的投入就开始增加，对吧？硬件设备以前大家没啥信心，那明年会推出 Vision Pro VR， 是一个更加轻量化的，很可能接 iPhone 的这么一款设备，而且成本会更低。那个时候我觉得初步就有消费者会比较喜欢的应用开始出现，然后再到2026年左右，消费级的 AR 我们就 MR 比较好，因为我们不知道是光波导还是这个视觉，就是 VSD 还是 OSD 会成为主流。现在不知道，我觉得是一半一半的概率，所以2个东西要并行。好，我这个报告讲的比较快就到此为止。我觉得大家如果有什么问题，我们可以交流一下。这也是我的邮箱，大家有什么问题，欢迎跟我交流。好，谢谢。
谢谢吴小毛博士先生给我们的分享，看大家有什么问题。
我觉得这个思路比较就跟以前自己有一些想法有些类似，然后我觉得你们做的还非常的挺棒的。然后就有一个问题，就是如何解决就是个人用户他应该比如说像你们办公室应该会有一些设备去做一些就是做扫描之后，它应该是有设备去做管控嘛，对吧？然后如果像比如说我们个人自己在家的话你们预想的是通过一个什么样的形式然后来做呢？因为我感觉如果单纯靠手机靠眼镜的话，会不会就是它可能不太够之类的？
对，我们这套 set up 其实现在是用 GoPro 的相机在办公区去采集3D 的场景数据，然后它对3D 那些资产的放置是在电脑上做的，但是接下来很快我们就会实现用手机扫描你的家里或者办公室，就可以实现这个定位和空间计算，然后摆放是直接在现场摆放的， 就是不会再在一个电脑上单独摆放，所以孩子也能够拿这套东西去摆放他的东西，比如说拿着他拿手机也可以啊，就他拿手机，然后扫完之后，他就比如说往这里放一只猫，然后他就可以直接在这里选猫，然后选完之后就直接确认就可以。他也可以带着一个XR 的设备，就走到他家里，然后就开始摆放他的东西，摆完之后他可以说，哎，爸妈我摆好了，你们过来玩吧。所以我觉得这个是接下来很快就可以实现的。
好，谢谢。
哎，你好，我想问一下，就是你怎么处理现实与虚拟之间的关系？因为实际中的话，它是需要很多数据的。然后你们怎么去采集，怎么去处理这些的呢？像你刚才说的那个智慧城市，这个我是清楚，因为里面好多数据需要采集的，而且也有相应的一些软件厂商做这方面的工作的，也是有的。
现在现实世界的数据非常复杂，不光数据体量非常大，而且它通常是用来交互和展示的时候，它是需要经过数据清理和数据简化的。所以我们现在会有一些自动化的工具和半自动化的工具来帮助这个开发人员和美术人员去降低它的这个增加它的效率。但是我觉得这块还是需要行业的努力去进一步把它做到标准化。目前其实还没有标准的解决方案，基本上是要不就是有的3D 数据有的像 BIM 模型较好质量的我们直接拿来用，有的要经过一些手工和半自动的简化，现在还没有100%自动化的工具来处理。但这个领域我觉得 AI 是能够起到关键性作用的，就是把一些重复性的，比如说减模、补漏洞，以及把一些纹理的分辨率的降低，这些能够释放人的这些重复性的劳动，我觉得非常有价值。所以这是我们接下来几年要努力的事情。它现在我觉得在解决，但是解决的并不好。
您好，就是我想问一下，就是您刚刚提的那个端云协同混合渲染，就这个不是太明白，就是说它，比如说我一个3维场景是说有一部分是云渲染出来的，有一部分是通过native 本地客户端渲染出来，然后把它叠加在一起嘛？这块可以稍微再介绍一下吗？谢谢。
对，其实我觉得下一代的引擎结构，它一定是端边云自动由引擎来分配算力的。什么意思呢？就比如说你拿了个手机，对吧？或者拿了个 XR 的设备，或者一个车机系统，它首先会调用本地的资源，然后呈现最好的效果。如果它发现资源不够的时候，它就会去找边缘的或者云的节点，来增强它的计算。然后这种计算主要还是以本地为主，但是云可以去增强它。最简单的方式就是，比如说我们的 virtual texture 来增强它的 texture 的分辨率。然后还有一个，比如说我们的贴图。像全局光照的贴图或者阴影的贴图，也可以在云端算好，再 stream 过来，叠加到本地。所以这是不依赖于云和边的一套计算构架。然后极端情况下，比如说我检测到我接下来半个小时或者几分钟都会处于一个高速的网络的环境，那我就会直接切成云端的计算，很可能。而且这些构架都不应该由开发者担心，它应该就是说我 prefer 这个 performance 还是 quality， 然后引擎应该自动来分配这些算力。
我是你好，就是感谢你分享。我想问一下，就是这个，就是这个引擎嘛，就对于一些，就比如说一些初创的一些小公司而言，就是说怎么样去使用，然后以及我所说的这个使用就是一种什么样的一种合作方式。然后另外一个的话就是它所对应的这样一个开发者的一个社区，目前是一个什么样的一个情况？然后，如果是跟 Unreal 和 Unity 这边相比的话，就是这一块引擎它目前所存在的一个优势，还有一个它的不足有哪些？可能问的比较多啊，不好意思。
没事，一个一个来。
好。
就我们首先这个引擎很可能明年推出。就是我们为什么不直接推出呢？我觉得一个引擎必须要在得到真正的较大规模应用之后再推出。就像我们的，如果一个游戏引擎没做过游戏推出，我觉得开发者用起来会比较难，所以我们计划明年推出吧。然后推出的时候呢，我觉得它的用户群体和 Unreal 和 Unity 有较大区别，就是 Unreal 和 Unity 还是这种较为专业的人士。我希望我们的引擎是那种有基本的，我们叫半专业用户啊， 就是没有非常强的那种游戏经验的背景人就能用，这是我们非常重要的一个目标。然后我觉得我们的最终用户群体就会跟他们不太一样。我举个例子来说，比如说商场里面的工作人员就能用我们的引擎去布他的那套销售系统，或者说 MR 的体验店的系统，还有家里的家庭主妇或者是家里的丈夫和孩子就能够布局他家里的这套体验，然后人人都可以在大街上或者说一些旅游场景来创建素材，因为它会更加智能、更加低门槛。所以这是一个非常重要的一个点吧。然后我们也会针对这些垂直非游戏的应用领域来推出我们的工具，比如说数字孪生类的标准工具，还有比如说影视动漫特效的，还有针对 XR 游戏的这些工具。但是不会推出针对现时代游戏的编辑器，那要3年之后最少。所以跟他们的差异化就是我们首先不会去做他们现在最重要的游戏的场景，就是现时代的游戏我们不做。我们看好的是下一代的开放世界的游戏，而这种游戏会更加的人人参与内容创作，然后更多的是低门槛的，然后大数据支撑的，更多人能使用的这种工具吧。所以我觉得区别还是比较大。
就是我刚刚也听下来，就是说你们后面是会推工具对吧？然后是 to C， 就是说给到一种普通用户都能用到的。但是如果说比如说想跟你们就是使用你们这个引擎，就作为这个开发生态里面的一员去做一些不一样的应用，就这个的话有没有一些计划和场景？
这个是在这个后面一步的，就是我们会推出，因为我们的其实游戏引擎至今都没有实现 SDK 化，我们往后会实现我们的 SDK 化，而且我们逐步会开源，就是我们一定会，我们叫逐步有序开源，我们先给我们的大 B 进行开源，然后再给开发者开源，所以一定是要走这一步的，我觉得否则这个引擎也不可能做得很成功。
这个有具体的那个计划吗？
还没有。
好，谢谢。
因为商业比较复杂，我们现在很难承诺说哪个时间点。
好。
对。
好。
但是一定是往这个方向走。
博士，感谢您的分享。我对引擎的渲染方面比较感兴趣，就是渲染的一些技术。我刚才注意到您说的这个引擎是基于实时的，并且是不基于烘焙的。然后我在想，它是否是用到了一些硬件加速的光线追踪，或者说是有计划引入这个硬件加速光线追踪？谢谢。
我们其实如果你在手机端有光追加速的硬件，我们是要充分使用的。但是现在手机端能有光追的这种设备并不太多，所以在云端和 PC 端我们是100%使用硬件加速的。
那这个引擎它的那个全局光照，因为您刚才说它是不基于烘焙的嘛，然后可以简单说一说全局光照的方案吗？
你说在移动端是吧？
对，移动端。
移动端其实是在一些，那也不是说完全，那个有一定的静态，有一定的预处理啊，就是我们会采一些光球，然后再去插值，所以是属于一种混合的方案。我觉得可以是半动态，就完全静态的我们很少用，因为烘焙时间太长了。就那个我们要求烘焙的时间要较短，所以那些采集球也是大概在秒级的速度完成计算。对。
好的，谢谢。
好。
你好，马老师，我想问一下，如果是实时采集的一个3维数据啊，你到了渲染阶段使用推理吗？就说渲染以后，把真实的3D 世界渲染成一个虚拟的世界，这时候会使用引擎中会使用推理工具吗？或者是有什么推理过程，把它实时的渲染出来？
您是说，就是采集现实世界的？
对，3D 的数据，对，视频也可以，或者就是一个3D 的场景的数据。例如我想采集一个就是例如刚装修完的一个办公楼或者怎么样，就是这时候我使用了一个3D 相机，工业级的相机来采集所有的数据，然后把这个数据转到你的引擎中来实时形成一个就是说虚拟化的一个世界，然后我们来去做一个 AI 就是说运用。这时候你在渲染过程中使用了某些推理工具，因为采集中可能会有数据不准确的情况，对吧？ 因为采集的设备也不一样，可能我会采用一些专业的工业级相机来采集一个3D 数据，它是通过色深来把三维数据是双目法嘛，就它会把一些数据产生以后，我是怎么来把它变成一个虚拟世界的一个过程，你能讲一下吗？
您这个就是采集到之后有2种方法进入我们的引擎，一种是把它进行3D 的重建，就是把它做成3D 的 mesh，3D 的模型，然后加上纹理，就这种你交互性就会更强。那如果你是一个偏稍微静态一点的场景，我们可以用 NERF 的方法，就这种神经渲染，对吧？就可以直接来呈现你的这些细节。那现在我觉得推理主要是小规模的应用，就是在一些半自动化的工具，我刚才说的，比如说进行一些大概的 mesh 的简化处理，还有一些简单的补漏操作，还有加入一些元素等等。但是总的来说，这一块做的还不是，就还是接下来要努力的方向，就整个行业都有努力的
对，
方向。
我就是刚刚听到，就是你是半自动化，并不是全自动化的一个推理现实渲染出来的一个。那大概什么时候能够给到一个就比较完全的这种就是推理的方式？大概要到明年吗？
不可能，我觉得这个最少是3年的工作。
3年的事啊。
就是一个较为自动化的，能够获取现实数据，不管是 NERF 渲染，还是说把它3D 化的，就 NERF 渲染的可能3年，如果是把它3D 化、实体化，还有全自动的，可能5到10年。对。
好的，谢谢。
但是这个非常有意义，所以我觉得开发者们如果能在这个方面进行努力，我觉得对整个行业和社会的价值都是非常高的。
那个吴博士您好，非常高兴今天能听到你的这个演讲，然后我也获得很多有意义的这个信息啊。您谈到了很多这个引擎的在这个商业领域的应用，我听下来可能是主要 to B 端的嘛。然后您之前也提到了有在这个未来可能对于个人的应用可能是有这个3D 的这样一个 App 出现在这个应用市场。那我在想，就是对于进一步的对于个人端的，就是to C 端的这个市场的开拓或者是应用，这边或是咱们公司有怎样的这样的一个计划，或者说从 C 端这边实现一个这个商业上的价值，有没有一些这个好的计划或者见解？谢谢。
好，谢谢。就是整个行业都在寻找这个3D 的爆款应用来推动整个混合现实的爆发。我们也思考了很多年，但是我目前思考下来唯一可行的，像对于我们历届来说，适合像终端公司，像华为、比亚迪荣耀等等还有OV、小米这些公司，甚至苹果，一起开发一个下一代的游戏。我认为这是唯一的突破口。所以我刚才有一个画面，就是显示我3年后做的那个游戏，就是我们一定要和终端厂商把这套交互做好之后，再去把游戏开发出来，才能带动整个交互和爆款应用的发展。这个游戏本身做成什么样子，我觉得我觉得一定是一个混合现实版的堡垒之夜，或者混合现实版的 Pokemon Go， 更高品质的 Pokemon Go， 有更加跨设备的Roblox。我觉得这种游戏化的应用，它也需要跟我们的衣食住行和工作完美结合。我觉得这种应用才是真正的下一代的爆款应用，而它非常依赖于终端设备的爆发。所以我们会和这些终端设备厂商来联合，一起来努力实现这个目标和梦想。
看看还有什么问题？
你好，吴博士，很高兴听到你的演讲。刚刚听你说那个，在那个VR 和 XR 领域的应用，现在目前的设备好像大部分交互方式都是视觉，然后如果后续硬件厂商有什么新的交互方式，你们这边有什么布局吗？
你说交互方式视觉是什么意思？
就是现在的设备大部分都是，就是只能看嘛，没有深层次的交互，
就是没有太多交互是吧？
对
对，我觉得你问完了是吧？就是交互本身是整个我觉得接下来整个人机交互要突破的最核心的一块。现在苹果的设备可以较为就是在3维空间的2D 平面进行一定的交互， 就它没有做到非常大空间的这种交互。我觉得明年这个技术应该就会取得较大突破，所以那个时候你的手势交互是非常自然的，甚至可能会包括比如说手环，或者说手表的，大家可以看到苹果的手表开始可以有手指的控制了，所以手表混合手环以及加上你的手势手指的交互，我觉得明年就可以实现，所以这个并不是最难的，我觉得难的是这个东西用来干嘛，就是消费者拿到这套东西它能用来干嘛，这个设备够不够轻，然后能不能为大家日常每天都想用，没有那个设备就像手机一样，离开手机好像，对吧？就非常不自在，要达到这种感觉。但是我觉得明年会是第二个阶段性的突变，
你好，感谢吴博士的分享。就是在建筑行业有个 BIM 建筑信息建模，就是说做这一块的话，就搞这种建模的话，是不是需要有一些各行各业的一种结合？比如说未来贵公司考虑就是和别的一些行业的一些结合嘛，就是跟扩展这个建模方面的一些渠道。
您说建模方面是吧？
对，比如说是你像 BIM 建模的话，它需要有工程学知识，有那个建筑学知识，对。
我们觉得，因为游戏引擎一般不用来建模，都是在 Maya、3D Max、SketchUp 的这种专业软件，对吧？或者 Nero 这种软件里面建模，所以我觉得游戏引擎它的建模功能会逐步的增强，然后它应该是从那些低门槛的工具入手，而不是从非常专业的地方入手，因为非常专业的工具制造周期极长，所以我觉得第一步会有点像，甚至比 SketchUp 还简单的工具集成到游戏引擎里面来，让大家可以简单的建模，甚至用一些手机扫描，然后进行还原的方式或者 Nerve 的方式来建模，后面才会反过来逐步的增强它的专业功能，所以最后才会把专业的这种建模工具集成到现在的游戏引擎里面，它是反过来的。
好的，谢谢。
你好，就是我想了解一下，像你们的引擎里面之前看到的像一些布料模拟，还有引擎提供的一些物理特性是你们引擎自己实现了一个物理引擎，还是说用了一些第三方的物理引擎呢？
没有，游戏引擎一般不会自己写物理引擎所以 Sebastian 这个 Physics Engine 我非常感兴趣，是吧？我觉得端云构架的物理引擎是下一代引擎必须要具备的特点，所以我们集成的是 Physics， 还有一些其他的开源引擎，所以一般大部分游戏引擎都是这么做的啊，因为它没有必要去自己做。
好，谢谢。
那我们上午的论坛就到此，下面是午餐时间，1点45，大家可以对感兴趣的还可以继续回到这个论坛这个地方来。好，谢谢大家。
So everyone, our next speaker is Mr. David Smith, who's the founder and CTO of Croquet. And he will talk about creating the next generation of a multiplayer with a Croquet. So please welcome Mr. David Smith.
Thank you for having me. Let's switch this one too so I can see. So I'm going to give you both kind of a history of why we created Croquet. I'm going to give a little bit of a deeper dive on why we did it, how it works. I'm going to do some demos. And then I'm going to talk about the deep details of how it actually works, because I think that'll give you kind of a good understanding. And then, depending on the time, I'll do a deeper dive on actual applications that we've built. This is the background of what we did. This quote is one of my favorite. Man is much more than a tool builder. He is an inventor of universes. This was by Alan Kay, who was my mentor. in a paper he wrote, which I consider one of the most important papers in computer history, A Personal Computer for Children of All Ages, where he describes for the very first time the idea of what we think of as the laptop today. So what I'm going to do is, first of all, give you a view of the future through what I call the lens of the past, because how we got here matters a good deal, and understanding where we want to go. These are the people I consider to be the heroes, the true heroes of the computer revolution, the people who created the world that we live in today. I think 1968 is the most important year in computer history because many things converged that year to really define everything that's happened since. And they were really crucial. I'll start with Doug Engelbart. You saw some videos before this that were showing him and others. Doug was a friend of mine from many years ago. He's passed away. He's known as the person who created the mouse, but in fact the mouse was a part of a much bigger system. And that system, when you think about it, the mouse was like the radio on your dashboard. It was a small part of what he was really after. Other things that he's known for, he invented the idea of Windows, hypertext, concept of bootstrapping. I'll talk a little bit about that. And in particular, most importantly to me, was this idea of collaborative computing. So his big idea is collective IQ, all of us being able to contribute and create together, was a crucial concept that actually came from the early 60s. This idea of like, how do we work together to solve very, very large problems? But in doing that, he formed this concept of bootstrapping, and that's the idea is the state of your technology allows you to better manipulate information, which allows you then to improve the technology. So that's actually a spiral, if you want to think of it that way, where we're constantly improving. One of the things he's known for was in 1968, he did a demonstration of his ideas that really had a profound, deep, deep impact on computing. This is a short excerpt from that. Hopefully we have the sound here. Hold on. I think we lost the sound over there. I'm going to just turn it back on. Just a second. Oops. I turned my glasses on. Oops, that's the wrong guy. Okay. So it was coming into my hearing aid, so I couldn't hear it.
And so this special thing, if I label 13, will switch over. So in his display, he sees my text. So I'll execute it. And sure enough, it does. But what's that running around? Well, if he's looking at my text, he'd like to have something to say about it. So we put on a marker, a tracking spot that he controls. So he's sitting there in mental park looking at this text, and he can point to it. But we've carefully reserved for me the right to control and operate on this. So my bug is more powerful than yours. But we can have an argument. Yeah. That's what they call a bug fight. So, all right. So in case you haven't been listening, Bill, we've been going through lots of examples and setting up in collaboration here so that we can go on into information retrieval. And we've set up now audio coupling, and then we're both looking at the same display, and that'd be very handy to work. We can talk to each other and point, and maybe later I could hand you the chalk on this blackboard, like saying, here, you control it. But let's stay this mode now and add another feature that hardware-wise is available to the kind of display we have. I'd like to see you while I'm working on it. So before I can do that, I'd have to set up my display in a certain way. Set it up so I see it over like that leaves a corner up there, and I say, now computer, do the automatic switching that'll bring in a camera picture from the camera mounted on his console, such as the camera mounted on mine is. Hi, Bill. That's great. Now we're connected audio. You can see my work, you can point at it, and I can see your face, and we can talk. So let's do some collaborating.
What's amazing is they were connected by a microwave connection between Stanford and downtown San Francisco. This is maybe the first audio video conference that remote video conference that was ever done. But the more important thing was they were actually sharing that screen, interacting with that screen together as if it was a single system. So what's truly remarkable, it was time sharing. It was online system, was NLS is what they called it. It had 192K bytes. It was a time sharing system, ran at about 1/2 MIP, but it supported 12 simultaneous users, had sub-second response, and is fully collaborative. Those guys really knew how to program. Second, 1968 was also the year that Alan Kay invented the idea of the Dynabook. The Dynabook is really, Alan's known as the father of the personal computer for a very good reason. Part of it is this device. He had worked very closely with Doug Engelbart. He spent a lot of time in his labs. So if you notice that picture of the two children, what's really important about that, first of all, they're both using Dynabooks, but when he envisioned this system, he thought of those two children working together, collaborating. If you look at the screens there, you'll actually see that they're actually playing Space War together. The idea, the original concept of the personal computer we think of today was intended to be multi-user, multiplayer. This is the system that he created with his team at Xerox PARC. This is the Smalltalk platform, really more than just it's not just a language, it's actually a kind of a full operating system. What's really remarkable is it defined almost everything we think of today when we use our laptops or our tablets or even our phones. It was all here. I'm going to just play a very short amount of this, but if I sat you down, 1978, that's I think 45 years ago, you would know how to use this already because you've been using this. Oops, back up. I want to play this.
Is used to select information. A window is selected by moving the cursor inside of it and pressing the first mouse button. A selected window displays above other windows, much like placing a piece of paper on top of a stack on a desk. Information in the window can be selected using this first mouse button. The selected information can be changed. Here, selected text is displayed as white characters on a black background. The selected text is replaced by typing on the keyboard.
I just find that, truly remarkable. That really, I think the most remarkable thing is very little has changed. He set something in motion that we're still part of, but we really haven't made substantial changes beyond that. This is Steve Jobs talking about when he saw that system for the first time.
And they showed me really three things. But I was so blinded by the first one that I didn't even really see the other two. One of the things they showed me was object-oriented programming. They showed me that, but I didn't even see that. The other one they showed me was really a networked computer system. They had over 100 Alto computers, all networked, using email, et cetera, et cetera. I didn't even see that. I was so blinded by the first thing they showed me, which was the graphical user interface. I thought it was the best thing I'd ever seen in my life. Now, remember, it was very flawed. What we saw was incomplete. They'd done a bunch of things wrong, but we didn't know that at the time. It's still, though, they had the germ of the idea was there, and they'd done it very well. And within, 10 minutes, it was obvious to me that all computers would work like this.
And all computers do work that way. So let's go back in time a little bit. Ivan Sutherland is known for many things, but perhaps the most important was the developer of interactive graphics via Sketchpad, 1963. But the other thing that he did was he set the bar for where we should be going. In 1968, he created the first real-time 3D graphics head mount with an ultrasonic tracker. By the way, one of my old boss, was the designer of that ultrasonic tracker, which is kind of cool. So I'm at 1 degree separation from that project, which is very, very neat. 65, he wrote this paper about the ultimate display, and if you're interested in the metaverse, virtual reality, you owe it to yourself to read it, because it's talking about where it will go, not where it is. And I think this is really important to understand the implications and the opportunities. 1965, that's pretty amazing. But here's a video of that system, and what you'll notice is it's not a VR system, it's actually an AR system. 1968, that's just kind of, to me, crazy, but here. So he's looking around in a virtual world. It's not a very big one. Today we might laugh at it a little bit, but honestly, it's pretty amazing. That cube, you can walk around it, he's seeing it, he's able to explore that, in this case, simple world. They made much more complex environments later, but that gives you a pretty clear idea of the nature. And notice it's a see-through display. You can see his eyes. They understood where it really needs to go. They're doing 3,000 lines at 30 hertz, which is at that time just astonishing. They had mechanical ultrasonic trackers. They had a specialized chip that would do this for them, and really was the very first AR device. So I'm going to now talk a little bit about, I gave you historical concepts where this stuff came from. Now I'm going to talk a little bit about the Croquet platform, because it also has a bit of history. This is the team that created the very first iteration. That's me standing next to Alan Kay. David Reed was our other partner, along with Andreas Reed, Rob. David Reed was the architect of the UDP protocol and co-architect of TCP/IP. Alan called him the slash in TCP/IP. His thesis was this concept of replicated synchronized computation that he originally formalized at MIT with the idea of real-time banking transactions. But Alan used to read everybody's thesis and had read that and said, this might be the ideal way for us to create the platform we wanted to do. So we got together and did that. This is actually a demo from 2003, so this is 20 years ago. But this is Alan and me demonstrating the first version of Croquet. So let me do that.
So I'll come in, block it, turn it into a fish. Okay, so what I'm going to do here is there's not enough fish, I'm going to create my own. So I need to grab a little paint package. And what I'm going to do is literally draw a little fish. Like so. Do a little bit of an eye. And a little bit of color there. And then paint that, and then
So what's going to happen here, by the way, is originally the work of Takeo Igarashi, who's now a professor at the University of Tokyo, was done for his master's thesis, I think, and it's pretty darn cool. Go ahead.
what I just did, this is the fastest and easiest 3D design tool you've ever saw in your life. Now Alan's going to make something similar. He's going to add a little sequence to it.
Yeah, so I should come over here. I'll do the same kind of thing. I'll go get a drawing tool here, and I'll do a much harder problem for this program, which is, what do we call these things? Seaweed? Seaweed. So you can imagine now the system is going to, basically what it has to do is it has to take these planar things that I'm painting and figure out the major and minor axes all over the thing regardless of what it is, and then use those as a way of spinning out the tiling for the thing. So this is we'll have to think just a little bit here on this one. I couldn't actually believe that this would work. So of course I never even tried to do it. Wasn't it your kid?
Yeah.
Dave has a kid, so here it is.
And it's coming over here. Thing to notice also is everything we make is automatically copied over. So I've got, I'll grab this and move it around a little bit.
Actually, it's not really copied, it's actually recreated.
Right.
Because this is a replication architecture.
So what we've done, it's a shared, I said earlier, this is a collaborative environment. It's a broadband conference call.
All of these things are scriptable just the way I showed you. I'm not going to do that right now. Basically, it's all scriptable. And while you're in the routine, one thing I
Anyway, this, if you saw Doug Engelbart's demo earlier, this is, in a sense, that grown up a bit. So when we started thinking about doing kind of the modern version of croquet, we were thinking, you know, the advantages we had and why we would do it this way. Tim Sweeney wrote, initiatives to place real-time processing on the wrong side of the latency wall have always been doomed to failure because even though bandwidth and latency are improving, local computing performance is improving faster. This is a big deal. This idea, you can't trade one for the other, really. So what's croquet? You kind of have a sense already. A bit identical synchronized simulation platform. Simulation code is right now written in JavaScript, although Rapier, as I'll show you, if you saw earlier, is written in Rust. The rendering, UI, visual effects, are all managed locally, and I'll talk about this. One way to think about, in fact, the way it is croquet is a model view controller architecture. Sessions are automatically synchronized between players. When a new user joins, it's automatically shared. This is a really big deal. So why JavaScript? I'm not going to go into too much detail, but JavaScript has certain features. There's a number of languages that share this. It runs exactly the same on every device. Why is that important? That means that if I do an execution of some function or something, some code, some object, it's going to run exactly the same on my phone, on my Mac, on my Windows, any device, my head mount. There are a number of languages that share that. Rust is one of them, which is one of the reasons it fits so well into what we were trying to do. Java is another. Smalltalk is another. And these languages then allow you to not worry about the target platform. It goes everywhere. We did have to patch certain things. IEEE doesn't specify what happens with the low bits of transcendental functions. We had to patch that. Also, the random had to be patched because you need a replicated random. Random's used everywhere in multi-user systems, games, and that sort of thing. And why not Rust? Well, actually, that's a good question. Part of the reason was we started this project before Rust was really much of a thing. Rust would be actually an ideal platform. We learned a lot working with Sebastian on integrating Rapier into Croquet, and I'll show you a little bit about that. But everything that we can do in the JavaScript side, we can do in Rust. So it's really just a question of finding the resources to do that. And we feel like that's an obvious next step for us, among other things. Here's a demonstration of Croquet. This is 2 users. You notice I passed by one of them. Now I brought them both together, so they're actually, I'm controlling them both. But you see that little simulation is running. I pick it up and move it around. This is a multiplayer asteroids game, and everything is synchronized. This can be any devices, multiple devices. This is a multi-user text editor. I'm just saying that right there. And it's perfectly synchronized. So all these apps are written in Croquet. This is actually a live Bitcoin visualization. We're grabbing data from a Bitcoin service. This guy is really interesting. That flamingos flying around. The code there says when actually I'm going to pause this. Oops, back up. Now I have to go find that. Sorry about that. Yeah, the code here, if you notice when you clicked on it, he paused. And so this code is really, this is live inside that system. This is a video here, but it was live in the system when you use it. And what's happening is we add an event listener and says pointer down, call the toggle function. Toggle function simply says, hey, if you're circling, stop circling. And then, so that's what's happening there. But I'm going to let it run again. And what you're going to see is we're going to, oops, we modified the code. I went too far. I want to back up just a little bit because that's pretty cool. I just thought that was just the coolest thing. So we're actually going to modify this code here. We're going to have notice it's multi-user, both sides, the editors being changed. And now we've got the flamingo flying backwards. We just changed the direction. This globe is another thing. We're actually grabbing all of the flights, all of the commercial airplanes in the sky at that moment and plotting them on this globe, so everybody sees all the airplanes. Those are, at the time, is that every one of those dots was an airplane in the sky. Oops, I gotta go back. Keep going. Oh yeah, I want to show you this. So we'll keep going here. Usually I do this live, but latency's kind of bad here. So now this is Portal. So I actually invented portals many years ago. So one of the users is going into the portal. Notice he changed into a cat, and he's looking around. But the portals are also kind of object that you can manipulate. You can drag them into a space. See, I'm moving it around. You can literally pick them up and drag them into another environment. They're just really just URLs. So they're just links. So that's one way to think about it. So I'm going to show you a couple of other demos. You notice that over there is a physics simulation. It's running on this computer here. And I have the same thing running on here on my PC. Now, what's really interesting about this is that they're not communicating at all. There's no, we're basically, all we're doing is telling both of these what time it is, and that simulation is fully deterministic, so anything that happens on one happens on the other. But one of the things we can do is I can create a new object. I just created that sphere, and you notice the sphere happens in both. There's a green sphere. So that display is this computer. This display is that computer. This computer here, this computer and this and that are the same. So I can actually play around with that quite nicely. And by the way, this is my phone with exactly the same simulation. So I can tap on this, and you can see the same thing on everything. So I'm going to show you the next thing. I'm going to switch to this guy. So what's going on here is this is a game, a demo game that was developed by Brian Upton, who works with me. Brian was the game designer for Rainbow Six. What I'm going to do, actually, I'll show you anything I do one place. So you see me making this, I don't know if you can see it. You should be able to see me making a tower, both on that display and the big one here. So, and then I'm going to start generating a bunch of bots, like so. So all these bots are being generated on both. Let me make sure, yeah, they're there. And what's really cool is everything is perfectly synchronized, but it's hard to tell because you see those little characters, and you can kind of see them side by side. But what I'm going to do is I'm going to put a camera on one of them, and so I'll let that go. And sorry, so I just added a camera, and I'm going to add a camera to this guy too, and they should be synced. Whatever you see on one should be exactly the same as what you see on the other, I think. So even though we've got 500 bots in here, but there's no information being passed back and forth. We don't have to send any information back and forth because it's running deterministically. But at the same time, I can still interact with this world. So I can, you see, I'm kind of destroying the world in front of us as we move. You know, I can just completely change everything dynamically. So it's a live world. It's not just, you know, it's not just a simple, oh, well, it's a clockwork. It's far more interesting than that. So I'm going to show you another one. This is, oops, spelled GOSIM. No, there we go. So, oh, I spelled it wrong. Anyway, it doesn't matter. So what's going to happen is I wrote this game in about a week. And yeah, it's not as finished and amazing. But I'm going to have this guy join. And so it'll be, in a second, there'll be two of us. And you see there's two of us there. And this is actually a co-op defense game. So I'm going to shoot these guys and whatever. But what I'm going to do is I'm going to X, Y, Z, Z, Y, and then you. This is just a few of the bots, but I'm going to start generating many more. So we've got 12 bots out there, but I just made 1,000. There's 1,000 bots coming out at us. It's probably behind me here. Yeah, there they are. And you can see that. So we've got 1,000 bots, all perfectly synchronized. And I'm going to prove that to you. I'm going to go to top view. So you see both of those are exactly the same. But I can still interact with them. I can still shoot them, although there are way, way too many for me to fight off right here. But you get the idea is we're able to share very, very, very complex worlds together at the same time. Here's some more coming over the side, and I'll switch over and oops, take them out. And notice, by the way, the missiles bounce off, and they bounce off in exactly the same way on both. Everything is perfectly synchronized. Oh, somebody's driving that. That's somebody joined me. Cool. Anyway, so you get the idea. Notice I'm running on a pretty fast VPN. If you're running this, you probably see a lot of latency otherwise. Okay, let's keep going. I'm going back to that. That's the demos. I'm going to talk now a little bit about how Croquet is different from traditional client-server architectures, and then I'll go into deeper dives on things. So traditional model is on the left-hand side, where you have a server, and then you have the view, the client. The server's on the internet side, so it's maybe at some sort of cloud or something. And the view is on your machine. So when you're playing multi-user, the server is the source of truth. And then what you see is basically the server saying, hey, this is what happened. The problem with that is you see the big black arrows coming down. There's a huge amount of data that has to be passed from the server to the view, to the client. And not only that, but it's a very disruptive kind of thing because basically you can do predictive models of what might happen, but the server is going to say, no, that didn't happen, this is what happened. Croquet is very different. It has a completely different architecture, and one way to think about it is removing the server from the internet side down onto the client. That shared bit identical single logical computer, as Alan Kay talks about it, is a shared virtual computer that's running bit identical without having to communicate, as I said. And I'm going to talk a little bit about that, of how that works in a sec. Now, this is a model view controller architecture, if you're familiar with those. The model, in this case, is that virtual computer. The view controller is the thing that renders, and it's the thing that allows you to interact. So you click on something, that's a controller. When you watch something, that's the view. But the intelligence, the AIs, everything that drives that world forward is in that virtual computer and that shared state. So the model is a single, as I said, a single logical computer. The view's interpretation of that model. So here's a number of nice features of croquet that why we like it and why we think you should check it out anyway. It's decentralized. One of the, it's decentralized at almost every layer, and the intent will be it's decentralized everywhere, top to bottom. So as I said, clients perform replicated bit identical computations. It's synchronized, as you saw. Events are replicated. So when I click on something, that message goes up to the reflector and is shared. I'm going to go into a little bit more about that. One of the things that's really important, and you saw that with the game, was that you can join in the middle anytime. Doesn't matter when. And what's really nice is the programmer doesn't have to worry about that. It just works. So this is literally, it's a kind of a micro operating system. I think Randy Farmer described it as a collaborative microkernel. It's very low latency. One of the reasons is we can put reflectors. Reflectors themselves don't have any application state at all. That means you can move them anywhere you want to, and you can make them very, very close to the game players, which means that one part of it, the latency drops because it's just closer, but the other reason is we spend no time in the reflector. There's no compute there. This makes it even easier to make a fully decentralized system. Notice it was cross-platform. I showed it on my phone. I showed it on these two guys. Usually I show it on a Windows device. It's persistent. If we leave this game right now and come back, we can come back later and pick up right where we left off. And it's secure. All messages are end-to-end encrypted so that even the reflector can't look at the messages. So you can't attack the system from the cloud. Reflectors are very tiny. You can run them on a Raspberry Pi, actually. Stateless, very secure, encrypted end-to-end. Our goal is sub 15 milliseconds everywhere. And we think that might be achievable. We know 15 to 30 is doable. Currently, we're worldwide on Google Cloud, and we've also deployed within corporate firewalls on Raspberry Pis. We've also deployed on Cloudflare Durable Objects, Verizon on their 5G MEX via AWS Wavelength. I'll talk a little bit about where we're going next after that. So this is worldwide, every place except China right now. So we want to change that. So synchronized events. This is kind of a deeper dive into the system and how it works. So I'm going to talk about kind of that. I showed you what it does, but this is where it gets really interesting. So the edge reflector, as I mentioned, has no state. The croquet kernel is those identical virtual machines, that single logical computer. And the view is what you see and what you interact with, the view controller. It's locally rendered. And notice the gray area is the client side. The white area above is the internet. So traditionally, we think of it as a server and a client, but that's not the way croquet works. The OS can be considered the reflector plus these virtual computers together. That one without the other is meaningless. So you have to think of it in those terms. And then, of course, the view is what you see, that's traditional. So what's going to happen is the user is going to interact with that view. He clicks on that, let's say, in some way, like I did when you hit the space bar in the game or whatever. What happens is we generate an event. That event is then triggers, gets into the edge reflector. Edge reflector creates a timestamp and redistributes that to all the virtual computers that are in that session. They get that message, and basically they do a computation of that, but actually all the previous queued up messages that might already exist. So this is one of the magic things about how Croquet works. You can send a message to yourself in the future that gets put into an internal queue inside that virtual computer. There's a number of reasons you want that. One is obviously you're saying to yourself, you know, turn 10 degrees in 10 milliseconds as an example. But the other thing is that queue of upcoming events is one of the things that gets persisted, gets saved. So when a new user joins, they can take that same they can take that same virtual machine, and it includes not just the instantaneous state, what's happening right now, it also has all the information about what's about to happen. So the update's sent to the view, and the view is updated, and the worlds are perfectly synced. So I mentioned dynamic joining. I'm going to talk a little bit about that real quick. So you notice when I started to play this Guardians game, the tank game, we started out with a single user. It's like this, and we're doing whatever we do. But one of the things we do about every 5 seconds of compute time, which isn't the same as real time, we take a snapshot of that virtual computer. So when my second computer joined the game, we also save all the messages that may have occurred from the user. So if I was hitting the space bar really fast and we made a snapshot, we might have made a snapshot before all those messages got sent. And so to update a new user, what they have to do is grab that virtual computer and play back the messages they would have missed that weren't part of that computation. So the first thing we do is copy that archived virtual computer state into the other user's virtual machine. He generates a view, and then we play back the messages that they missed, and now they're synced. That's how it works. Okay, and snapshots, every snapshot is defined almost exclusively by external event, compute, external event, compute, external event, compute, external event, compute. And what that means is the end state is something we can snapshot and save. What's nice is not only can it be used by the new user joining while the system's running, but it's also persistent in that if all of us leave and come back, you can join exactly where you left off. You don't miss anything. You don't miss a single event. So I'm going to do a bit of a deeper dive. Let me just check the time because it's 2:28. So I got about 20 minutes to kind of review some additional ideas here. And I'm going to do this. So everything I'm showing you is available and open source. One of the things we've recently built is Croquet for Unity. We're really, really happy with it. It's still, it's in its final beta. It's basically at a golden master at this point. But it allows you to build very, very high quality games using Croquet and Unity as a very, very fast rendering engine. So the Guardians app actually, I showed you the web version, and we also have a fully implemented Unity version, which you can download and get access to all the sources and play with it. We have a number of other apps. I already talked about this. I'm going to talk about a few key ideas here. I mentioned this idea that we actually have an internal queue. When you have this virtual machine, we have an internal queue of all the future messages. And in fact, that's how you do it. We say, do something here. This.future 100, do something. This is kind of a little trick that we learned. This is, I could call it temporal tail recursion. So what's going on is we do something, we execute some code, and then we say, hey, I want to do it again in 100 milliseconds. So what we do is we call it this.future. This is JavaScript, by the way. So if you're familiar with that, if you're not, I'm pretty sure Rust isn't that different. This.future 100, do something. And what it does is puts that message into a sorted queue, sorted by time, of course. And so when it executes, it's going to call the do something function again, which is also going to put itself back into it. So this is how you do kind of an infinite loop in time. We also use a publish subscribe model. The reason is, so we have the model in view. In JavaScript, the view can actually read from the model. You never want to write into the model for a very good reason, which is if you did, you would break the consistency. Basically, you'd have the system diverge. So whenever you want to write something into the model from the view, when you click on something, what you want to do is publish that event. That event then goes via the reflector. Reflector puts that timestamp on, redistributes it, and everybody now has that same exact event at the same virtual time. So publish is a real key thing. And of course, on the other side, we do a subscribe to listen to that. So I'm going to keep going. Say listen is a shorthand version of that. We have an entity component model where you can just do a say listen. This object is connected to this object on the model view side. It's just a shorthand for managing that. I'm going to skip all this. No, we have on the Unity side, and actually on the JavaScript side, a number of tutorials. I'm just going to jump through these, just kind of give you a sense. This takes you right through everything you need to know to do the Unity application. So we've got a number of tutorials, but I want to just talk about briefly. This is a simple one. You're just using the keyboard to move your block left and right. And this is the code. This is all you need. One thing to note, and you probably saw this earlier, there's no netcode here. You don't need it. Since we're running a bit identical shared simulation, you do not need to specifically say, send this message. We do have the subscribe, and that's just listening to those transformations of state. And you do a publish, but it's really just communication between the model and the view. You don't have to think about it in terms of, I'm sending a message out there, is it going to arrive? I'm sending a message out there, does that trigger something else that's going to send a message that, in other words, there's no race conditions. It's a well-defined executable. And next is this guy where we do parent-child relationships. Not much different, actually. There's a little bit of extra code for defining a child with a spin. This one is just that. We're spinning the objects around. It's basically, step of creating almost anything you can do on multi-user. But one of the things to notice is there's almost no code. To give you an idea, the entire Guardians game for all the logic is about 500 lines of code for everything you saw there. So you can create much smaller applications that do much more this way. This is creating objects, clicking on them, and they kind of balloon up, and then they kill themselves. Anyway, all this document's available online. If you go to croquet.io and the Unity side of it, you'll find every bit of this. All these demonstrations are available for you to play with. So this is a simple avatar application. And then I'm going to go a little further. This is obviously using Rapier. This is the demolition project that we did. We've been working with Sebastian for a few years now, and it's just thrilling, how easy it is to build this kind of application, and it's multi-user. Everything you see here works perfectly synchronized. So thank you, Sebastian. And then this is the Guardians app, and again, all the source code for that's available. everything's there for you. So I'm going to switch back to a few, just talk a little bit about what's next. First thing is we're converting the system, we're making it fully decentralized. If you know what a decentralized physical infrastructure, what we're doing is taking our reflectors, and if you're familiar with IPFS, interplanetary file system, where anybody can host a part of it, we're going to allow anyone to host a reflector or reflectors, and then in return for that, and of course it'll be all open source, in return to that, for the hosting reflectors, you'll get paid tokens for that. So our current deployment looks kind of like this. We're actually a broader footprint than this. But once we deploy the reflector network, then what happens is two things. One is the cost of using this multi-user platform drops dramatically a lot. And the other thing is the deployment goes way up, which, as I said before, our goal is sub 15 millisecond latencies everywhere. And if you do multiplayer, you understand that that's crazy. But we think it's quite doable with this approach. The other thing we're doing is, and this will be sometime next year, I think. Currently, when the first user joins, we find the reflector close to them, which means that the other users are at something of a disadvantage if they're far away. So for example, if I join in North Carolina to reflector, I'm going to find either one, South Carolina or Richmond or something like that. And if I then choose to connect to somebody in Hong Kong, their latency is going to be on the order of 160 milliseconds, where mine is going to be 15. And so what you need is a way of managing that. And of course, you don't want to, punish the guy who's close by, but you also want to have a vehicle to make the other people a little bit better, a little more competitive, if that's what it is. Or if it's a multi-user application, they're doing a lot of work. So what happens is we have reflectors over there, and we can actually dynamically switch reflectors. We can do that. We believe we can do that in just a few milliseconds, and no one will notice. So that's the other thing that we've been working on, and that is the end. I have until 3:45. I can't do 3:45. It's been that long? Oh, I thought this was already 2 hours. Yeah, I can do that. Or actually, we can do Q&A now, and then I can kind of do deeper dives on things. So let's do that. I'm going to open it up, and if you have questions, happy to.
Thank you, Mr. David, for sharing. So I have a question. I know you used to be a Lisp developer. I also love the language. So I'd like to ask you a question about the history. Why did you start as a game developer in 1987? I mean, the cloning.
Yeah. So, oops. So that was interesting. I was very interested in games. I had an Apple II, and I tried to build a game on that device, on the Apple II. And I thought I wanted to have this world I could walk around inside of. And so I had these tools that let you paint the world. And in those days, the discs were quite small. And so I did like 10 frames of this game, and I ran out of disk space. So this idea of, I wanted to go through a cave, and I just immediately ran out of space on the Apple II. And so I realized that there's no way you can make anything interesting that way. And so I'd been kind of playing with 3D at that time, and I realized that I could utilize 3D as a compression technology. So I started working on this, there was a fantastic book at the time by Bruce Artwick talking about microcomputer games. He's the person who wrote Flight Simulator. And so what I realized, for example, was if you have a grid, grids don't take up very much space, and you can sort of think of it as one byte of information can give you a huge amount of data about what's in a square, in a grid. So it can say, hey, there's a door here, or it can say, hey, there's some object on this, and it's literally you have a way of describing that information about the walls and that sort of thing. It's just the bit. There's a bit, that means there's a wall here. There's a bit, that means there's a wall here. And so what happened was I figured out I could make an entire level in 4,000 bytes. Now, that really mattered because I wound up switching over to the Macintosh for my first game. I got my Mac February 11, 1984, which is the first day they were available. And that idea allowed me to create a very, very, very large game in 400 kilobytes of storage on a floppy disk. And so, so we actually had something like 8 different levels. Each level was huge. Actually, they were so big that people. Also, the game was very hard. It was a very hard puzzle game, but people would spend up to 2 months exploring that world, exploring that game. It was crazy large and crazy hard, but it proved a couple of things. I think it was literally the very first first-person shooter adventure game. In fact, there's a documentary out that just came out a few months ago called FPS, First Person Shooter, and I'm featured in that. So that actually led to 2 really important things, but I just want to finish this. So when we did that, it kind of changed what people thought was possible on a computer. It's like, I remember I was working on this and people were telling me it's impossible to do 3D on those kinds of computers. And it was hard, but it wasn't impossible. A good example, Bruce Artwick came up with this really clever idea. I should mention the Macintosh was 68,000 CPU. It did not have floating point. So everything was fixed point, if at best. So doing things like sine cosine computations is impossible. You couldn't do it fast enough. So the way we did it was you make a table of sine functions that was 265 bytes long. Each sine was, each index was 8 bits. And so you had an 8-bit sine table is 256 characters long. Why is that interesting? Because if you have a 1 byte as the direction you're looking at, saying it's 256 pseudo degrees. It's not 360. So that means that 1 byte has 1, 2, 3 up to 255, 0 to 255. And then what's really magic is if you add 1 to 255, it goes to 0. So you're able to spin around. You basically have, and so you get that, but then you do the sine lookup. You say, what's my angle? It's 0 to 255. You do the index, and now you've got that. But then what's the cosine? You add 64. And now you've got the sine and the cosine, and now you're able to do a rotation of the first square. Now, why is that nice? Because you do the rotation of the first square, now you know what the dx and the dy are, and so you can just add those to get the next square. So if your world's built on a grid, you can actually convert the entire computation of everything in that grid to that sine cosine trick, and then a bunch of adds to completely fill out everything. Of course, there's another part which was you had to do the perspective correction, which was, you had to do what's equivalent of divide, but then it was just another lookup table. So what's the distance? Well, you just look up on this table and then you know what the height is. The other thing that was neat is I cut the world in half, so to speak, so I can compute actually I think I computed the top and then you subtract by whatever the height is and then you get the bottom, so you get both of them at the same time. So the harder ones were actually the characters, because the first real-time 3D objects in a game was that. Also the first crates were in that game, I'm pretty sure. And so those were tricky, but since there were a few of them, you could do quite a few. There was no Z buffering, obviously, but that's how that got done. That led to two really interesting things. First, Jim Cameron, the director, was working on a movie called The Abyss. He saw a pirated version of my game and asked me to help him visualize the set. And so he sent me the blueprints of the movie. And I built that set so he could actually walk around. The very first time anyone was able to walk around inside of a set before it got built. And he figured out that a whole section of the set, it's a complex set, by the way, a whole section of the set was never going to appear on camera. And so they didn't need to build it, so it saved him $2 million. So it was, I'm still waiting for them to pay me, by the way. The other thing that happened was Tom Clancy, the author, got very engaged with the game and started calling me about once a week. He never asked for hints. He just wanted to yell at me because it was hard. But he actually finished it and was very excited about what it was and the technology. And he asked if he could work with me in some way. So he became, I started a company to do real-time visualization for Hollywood, set designs. Virtus Walkthrough was the product. And so he was my outside investor and board member. And then he introduced me to the FBI hostage rescue team in Quantico, Virginia. These are the people when bad guys take, prisoners at banks or something. They're the ones that they call on. And they used my software, but they took me on their training missions. And it was amazing. They have what's called a battle town. It's a big cinder block town. And there's an observation tower overlooking it. And they had these big black helicopters fly over our heads. And the black-clad ninjas coming down on the top of the buildings, and they start blowing things up. It was amazing. I was just like, this is better than a movie. So I told Tom we need to do a game on these guys. And he said, you do a game, I'll do a book. And that was Rainbow Six. So we created the Rainbow Six franchise and the Ghost Recon franchise. So I started a company called Red Storm Entertainment that, I think it's not quite the same anymore. It got sold to Ubisoft and they kind of dumbed it down, but at the time it was probably the most realistic real-time 3D shooter. That was done by Brian Upton, by the way, who did he did the game we saw earlier, like that Minecraft game. He built that. Anyway, so that's kind of the story of how we got to here. When I did walkthrough, it turned out Bonnie McBird was working at Apple at the time because I had written it for the Macintosh, and Bonnie was kind of consulting to Apple, among other things. But Bonnie's interesting because, first of all, she wrote a movie called Tron. I don't know if you've ever seen that. But she was married to Alan Kay. So she introduced me to Alan Kay, and this was around 1990, so it's a long time ago. And we started collaborating Yeah, Alan saw what I was able to do. Of course, I knew Alan very, very well. And so we started collaborating then. I did the very first version of what turned into Croquet in 1994. And then we joined forces full time in 2000 to build that version I showed you earlier. So that's kind of the story of how that happened. And it's been quite a ride. I've done other things besides that, obviously, but that was, I think, the most interesting projects, because I became very obsessed with this idea of enabling what I call an augmented conversation, where you and I are speaking, and what you see is what I see. What I do when I say something, we have a fully empowered AI. It's able to interact and modify things, but you see it as it happens. So it's sort of like, the idea is, if I pick up this object, which is real object, move it around, you see that. If I modify it, crush it, you see that. We want to do the same thing in the virtual space. Everything has to be bit identical. It's as if, the way I think about it, there's no physical reality, there's no virtual reality, there's only reality. And in the near future, we're going to be wearing glasses that allow us to merge those seamlessly, so you don't care what the difference is. Anyway, that's kind of a brief history of a lot of this stuff. But I'm happy to go deeper on anything you like. Any other questions? Yes.
Thank you for the inspiring presentation. So you mentioned the new joining player receiving the snapshot. So who's sending the snapshots to them?
Yeah. So the snapshot's actually kind of co-located with the reflector. It doesn't have to be. It's kind of can be put in a database. In fact, we save all of them. So one of the neat things about Croquet is, if you want to go back in time, you can literally load one of the earlier snapshots,
right,
and then play that forward, and you can literally see. You can use this for debugging, for example. You can play back from the beginning of history. So that this game that you have up there, you could actually go back to the beginning before anybody was there and play it all the way into the future. But the snapshots are, what we do, by the way, is it's an object-based, the model is object-based, and so we just traverse that model and create a JSON file. The trick is to have it so that it's bit identical when we decompress it, when we put it back together. But we do that. So that means then that when you join a session, we just ask for the most recent snapshot. We load that, we decompress it. Like I said, we play back all the messages. But yeah, it can be anywhere. In fact, the new architecture will it'll probably be decentralized. We'd like to use something like IPFS, but it's too slow right now. You want to have a much faster load than what IPFS would allow.
So if the snapshots are from the reflectors, does that mean the reflector also has the virtual computers?
No. All it has is that file and any messages that are associated with it. So, and that's just an arbitrary place to put it, by the way. It doesn't have to be by the reflector. It can be some other service that you set up. But yeah, the reflector has no application state at all. It can't even read it can't even look at the messages. All it can do is take a message, because the messages are encrypted. All it can do is take the message, put a timestamp on, and then redistribute it. So there's no way for it to actually, it can't have any state.
Like a relay server.
I'm sorry?
Like a relay server.
I didn't catch that.
I mean, relay server.
Exactly what it is.
I see.
I call it a reflector, you can call it relay. It's like, that's it's not the same exactly, because, like I said, it puts a timestamp on that message and redistributes it. It puts some other metadata on it too. So
Okay.
for example, there's a counter. It's like you count message 1, message 2, message 3. And so you want to track that as well because you want to make sure did I miss any messages. If I get message 3 and I get message 5, that means I missed message 4. However, we use TCP, so that never happens either. There's never a problem. It uses WebSockets.
I see. So my second question. So in the Unity ecosystem, there are other similar solution like Photon, right? Photon. So could you give some
Photon's
comparison?
quantum system is kind of similar.
Mm-hmm.
They don't quite work the way we do. They actually have it's a kind of a hybrid. They have first of all a predictive model. We don't do. You can do some prediction, but we don't do that. And they also have a rollback. Rollbacks are the most expensive thing you can do in computing. So it's basically if something happens, you do something local with the predictive, and you say, I want that not to happen, you have to roll it back. And so they actually have to create modules themselves to be able to provide that. Croquet doesn't have that issue. We don't, first of all, we don't necessarily do predictive like that because we're depending on very, very fast, very, very low latency. And that actually works pretty well, especially since the view and the model are not intimately connected. So the view can be instantly updated. You know, if we play that game, the tank game, there's no delay whatsoever when you're moving the tank or when you shoot. It's instant. But what's going on is we're sending a message to the reflector is sending everybody back, including to you, hey, this was what happened. You ignore it because you're the one who generated it. But everybody gets that message, and all the events are perfectly synchronized. So when I shoot that missile is now in replicated space once I do that. And so it's moving, and any collisions that occur are happening in replicated space, in multi-user space in the model. So that actually works like a dream. It's much, much easier. You know, anytime somebody mentions rollback to me, it's like, okay, you just killed yourself. It's the worst. It's the worst thing that happens. And remember, you're running at 60 hertz. You know, rollbacks at 60 hertz are insane. You don't want to do that. No one wants to do that. So I think that they're figuring out a lot of this stuff, but they have a long way to go before I think it's going to be something. And they're very constrained about how they're rolling it out too. I can see that they're struggling with that model. It does some things nice, but I think you know, we built a much more general purpose approach that is a lot more flexible, and especially when we start adding these next generation capabilities, like obviously decentralizing the reflectors completely, where anybody you can host a reflector on your computer, and somebody, your next door neighbor, can use it, and it'll be seamless. And the other thing is the latency balancing, being able. This is like one things you can't do with centralized server architectures because they own state. Anytime they have state, you can't move it across to another continent. But reflectors don't have any state, so you can move it from here to there in very, very quickly.
What happens if a virtual computer receives an event that was frames back from its current frame?
It doesn't work that way. Time increases monotonically. So what will happen? We never get out of order, and what will happen though is if you have a lot of latency. So like I'll tell you a good example is communicating between here and outside the firewall. We get like 500 millisecond latency because they're looking at all the bytes, I guess. And so what that means then is the experience is degraded because that means you've got more latency in the system than you'd like. but it never gets out of order. You could actually have a croquet session between here and the moon, which is about 2 seconds away. It will work perfectly synchronized. But whoever's on the other side, let's say the guy on the moon's using an Earth-based reflector, is going to have a 2 second delay from the time he clicks something and then he sees it. It might be 4 seconds because it's a round trip. So latency is a problem, and like I say, you can do predictive models, but then you have to deal with a different kind of problem that actually can cause more issues. If you have the ability to move the reflector around, then what you can do is literally have the reflectors bounce to the moon and back to the Earth. So I'm using this reflector here close to me when I'm the guy doing it, and I can pass it over to you, and now all of a sudden you're fast. Having everybody fast is harder, but there's ways to do that too, but that means having multiple reflectors that are in disjoint spaces. In a way, mirroring some of the stuff that Sebastian was talking about with the way he manages computations for physics.
Okay, thank you.
Any other questions for David? All right. Yeah, thank you, David, so much for sharing your knowledge and your experience. Thank you. And everyone, we have one more session today at 4 p.m. We have Mr. Jin Kun from Cocos. So if we have a little bit longer break, please everyone be back at 4 p.m. for the Jin Kun Cocos. Thank you.
We would like to remind you again to switch off all mobile phones and put electronic devices to silent mode. Thank you for your cooperation.
So everyone, welcome back. And our next speaker is Mr. Jin Kun, who is a graphics expert at Cocos. And Jin will talk about scalable graphics and rendering pipeline in Cocos Engine. Welcome. Thank you.
大家好，我是金坤，我在 Cocos 负责就是图形渲染相关的这些研发的工作，然后很高兴今天有这个机会跟大家做这个分享。那 Cocos 呢是一个开源的，然后底层跨平台的引擎，然后它有 C++ 和那个 TS 2套实现，然后我们的 feature 也是同时兼顾了3D 和2D 项目的一个开发，然后主要的应用行业呢包括说游戏，然后还有这种智能座舱，就是车机。然后还有元宇宙，还有 AR、VR 等等。先给大家看一下那个最新的3.8的版本发布一个演示视频吧，可以有一个直观的感受。
我用 Cocos。
我用 Cocos。
私も Cocos を使ってます。我用 Cocos。
我也在用 Cocos。
我也在用 Cocos。
我用 Cocos。我也在用 Cocos。
首先，作为一个游戏引擎呢，这里会有一些游戏的代表案例。那前一阵子爆火的那个羊了个羊，不知道大家有没有玩过？那个就是用 Cocos 做的。然后这里我说一下，就是在左边这个 Nano， 它是育碧的一个多人在线的一个冒险游戏。然后除了育碧之外呢，就是任天堂还有 SE 这些大厂，其实也都是有用 Cocos 做一些产品的。那么右边的这个是口袋骑兵，也就Top War， 然后这个在海外的排行榜非常靠前的，然后到现在为止，全世界已经有超过1亿的下载量。然后中间的这个呢是种地勇者，这是我们一个比较成功的一个3D 的标杆案例。然后呢，它登顶 App Store Free， 然后在其他的地区的应用商店上也都有非常靠前的排行。那除了游戏之外，就是在元宇宙还有其他的领域都有一些标杆的案例。这是美的的一个多人在线会议的一个应用，然后它是基于 Web 端的，效果还是挺不错，然后分发也非常的方便。大家如果有兴趣的话，可以进入上面那个最右上角那个网址，可以进去体验一下。这些是一些那个社交的 APP， 比如说右边的那个是 Discord 的一个社交的小游戏，然后呢，微信的之前那个兔年的新春表情包也是内嵌了 Cocos 来完成的。然后其实现在微信所有的表情包几乎都是用 Cocos 来做的了。中间这个。要想适配这样就是多行业，然后又是跨平台的应用呢，这个其实是需要引擎在各个模块上都有比较强的扩展性的。那今天我主要讲一下就是 COS 引擎在图形渲染上面的新的特性，然后以及它是如何适应不同领域的开发者以及不同类型的项目需求的。我会从一个高适配性的材质系统以及它的资源导入，然后说到灵活的 shader 的开发和渲染管线，大概会分成这4个部分来讲。首先是材质系统，材质主要用来描述我们就是现实生活中见到的这种物体表面的一些光学属性。然后我们先了解一下，就是我们是怎么样看到物体的。首先，光线会从光源发出，这个光源呢可能会有，比如说太阳这样的平行光，然后有天空这种环境光，也可能会有这种，比如说灯泡啊，或者是手电，或者是像投影这样子的面光源。那么到达物体表面之后呢，它可能会被吸收、反射、散射或者折射，然后经过这个过程之后，有一些光线可能会逃出来，然后到达相机或者眼睛，这样我们就可以看到它，大概是类似于这张图。我们可以看到那个红色的物体是光源发出的光线，经过1次反弹就可以进入眼睛的。然后有些白色的物体会反弹多次，那么1次反弹就可以进入的这种叫做直接光照，然后多次的这种我们可以把它叫做间接光或者是全局光。那么在整个过程中呢，我们就是作为材质系统来说，它更关注的其实是第2条，就是在物体表面发生的作用。那这个作用呢是需要用数学模型来描述这些事件，然后进行相应的计算。当然就是计算越精确越复杂呢，看起来就会越真实可信。那我们把这个计算的过程大致拆分为就是计算方法，就是第1条， 计算方法，就是像光照模型，我们叫光照模型。那么对于每一种计算模型呢，它都会有自己独特的一个参数集合。那这个就是第二部分，叫做材质参数。然后会将光照模型计算的结果和材质的参数合并起来，最终作为一个最终的呈现。这个就是第三个部分，叫做着色模型。我先来讲一下，就是第一个光照模型。那现在就是业界主流的这个光照模型呢，大概分为2类，就是一种是根据实际的现象，或者是根据美术想要的那个结果进行一些经验的或者是参数化近似的模型。比如说像柏林缝这样的，它可能是去描述表面比较光滑，然后有一些高光反射和光斑的这样的物体。那还有就是非真实级的渲染，比如说像卡通渲染或者是一些水墨渲染这样子的。但是现在业界比较主流的还是基于物理的一个光照模型，就是 PBR。那么它考虑了就是物理相关的很多的光学理论，然后可以更好的表达物体表面的一些光学现象。这样的好处是呢，可以适配更多的物体，它都可以用同一套这个光照模型来描述。那么当然计算量也会相应的会大一些。对于不同的光照模型来讲呢，它会有不同的参数集合。比如说经验模型可能需要的是美术去绘制的一些经验性的一些数据，然后它不一定有什么道理，可能就是看着像就可以了。那么对于物理模型来说，它更多需要的是偏向物理的数据，比如说这里的反照率，然后还有包括粗糙度和那个垂直方向上面的那个反射光强分布，这些其实都是比较物理的一些参数。那么对于经验模型来说，它的缺点是计算量比较低，但是它是就是优点是计算量比较低，但是它的缺点是适配性不够好，然后它会更带有倾向性，可能没有办法用在所有的物体上面。但是考虑到说写实材质最好是使用支持面尽可能广的光照模型，所以我们为了应对多种多样的项目呢，我们最终还是选择了 PBR 的物理模型。下面我针对不同种类的常见材质呢，给大家做个介绍。第一种就是我们大多数看到的那种不透明的物体都是这样的，就是光线在到达物体表面之后呢，它会被反弹出去，然后这个分布大致是呈一个上半球的一个分布，这种就是反射光。然后常见的就比如说金属和塑料这样子的这样的材质。那么对于各项同性的表面来说呢，那个反射光可能会绕着法线对称，然后它可能和那个法线夹角关系非常的大。那么我们可以看到一个圆形的光斑，可以在这2张图上都可以看到中心有一个圆形的光斑。对于室外的材质来说呢，可能自然界的材质，比如说岩石，然后地表，还有那个树木，还有木纹，这些东西也是比较典型的这种材质。还有一种是它可能在物体表面有一些细微的一些规则的条纹，然后这种情况下呢，反射光就不会再绕法线对称了，它会沿着那个细纹的切方向去分布，那么它会呈线状。在宏观的表现上面，它的高光是发散的，就比如说头发，然后头发的高光呢会沿着发丝的方向来分布，可以看到很明显的随着光的夹角，然后它的这个高光光斑也会上下移动，沿着发丝移动。这种我们把它叫做各项异形。然后还有一种常见的物体就是这种纤维织物，就是因为它有那种比较光滑的丝线，然后那光线会沿着，就像可以看到那个袖子右边的那个光斑，它会沿着那个纤维来分布。还有一些就是比如说这种笔记本的盖子可能有那种拉丝工艺的那种金属，这种也是类似的各项性的分布。然后这个演示里面呢，它的正面是拉丝的金属，它背面是具有不规则一些划痕的一个各项同性的金属。大家可以看一下它们的区别，这个是有圆形光斑的，但是这个的高光是呈条纹状发散的。像光碟也是类似于这样子的材质。然后我们可以通过改变材质的参数呢，来更改这种细纹的分布、条纹的分布。 然后甚至可以去增大，就是让这个细纹变得更深，或者让它看起来变得更浅。然后它会恢复成一个各项同性的材质。还有一些常见的就是经过加工的物体呢，它可能表面是刷有一层透明的清漆的。那这种其实是属于比较特殊的这种多层材质了。那它总共有2层，我们可以透过上面的这个清漆层呢，可以看到折射下去的底层的这个材质。那每层之间的光线分布呢，其实都是符合菲涅尔定律的。那最典型的，比如说钢琴烤漆。那我们就是因为有清漆层的存在嘛，所以我们可以很清楚的看到表面有非常清晰的这种反射。但是呢，又是因为双层材质它分散了这个光线的分布，所以反射也不会特别的强。底层的那个黑色也是非常明显的。所以如果我们按照单层材质去处理的话，可能它看起来更像是个镜子或者是不锈钢这样的东西，就不太会像是烤漆。还有一个常见就是车漆了。车漆也是类似的这种双层材质，然后它底层因为有金属漆，所以可能里面会混有一些金属粉末，我们可以在那个车的表面看到有这种闪亮的这种小斑点。我们甚至还做了一个就是在下雨天模拟的一个动画。然后因为这个车漆它是一个疏水材质，那么在疏水材质上面的水层其实也可以认为是跟清漆是类似的，所以我们只需要简单的改变那个清漆层的法线，就可以做出这种看起来是还挺真实的这种模拟结果。除了这些之外呢，也有就是有些物体它表面是带有绒毛的，然后就是比较光滑的绒毛。那么光线会在这些绒毛的纤维管内发生一些折射和反射，也就是我们叫内反射。那这样会导致表面会有一层额外的高光，然后看上去它就非常的闪亮。比如说这种丝绒的布料。还有一些油亮的毛皮，可能也都是属于这种类似的。你可以看到它在这个表面会有一层像附着的这种高光一样的，然后这个就看起来很有质感。如果我们把这层高光把它去掉的话，它就会变得像一个普通的布一样，就不会像一个丝绒。另外还有一些物体呢，它除了上半球的反射之外呢，它还会折射到物体的内部，然后我们也就叫做下半球的一个分布。这种物体通常看起来就是半透明的，但是一般来说，对半透明的物体，它可能反射和折射它都会有的，不会只有一种存在。那反射和折射也是符合菲涅尔定律的。有的时候我们可能计算折射比较复杂的情况下，就会用半透明来简单的去替代这个计算。尤其在那种光滑和平坦的物体上面，这样看起来效果也差别不会特别大。最典型的材质就是水面。如果我们平视的话，可能更多的是反射光，可以看到水面的反射。但是如果我们是垂直的往下看，就很容易看到那个清澈的水底。还有车玻璃，玻璃也是这样子的材质。是最后一种其实也是最复杂的，就是散射。这个光线呢，不单会穿透到内部，它又有反射又有折射，然后还会在内部发生各种作用，然后经过很多复杂的路径之后，它再穿出来，就像右面这张图一样。那散射的计算量是非常大的，计算也很复杂，所以我们可能需要预先计算好一些传输的数据，像类似于 PRT 这样的方法，或者是用相对这种实时渲染来说，可能用屏幕空间的卷积可以极大程度上的减少计算量。 最典型的材质就是皮肤。这个是切换散射光，可以看一下它那个耳朵上面的那个透光。然后还有就是眼周和鼻子附近的那种朦胧的散射的感觉。如果关掉的话，就整个皮肤会显得很干枯，没有生气，就不太像皮肤了。那另外呢，就是常见的也有这种叶片，因为散射光会随着那个穿透的厚度来进行衰减，所以因为叶片它的那个叶脉和那个叶片本身它的厚度是不同的，所以我们可以透过散射光清楚地看到那个叶脉的分布。然后还有这种玉石的材质也是一样，它会厚的地方会暗一些，然后边缘薄的地方会稍微亮一些，再加上表面这种光滑的高光，然后看起来还是挺漂亮的。刚才我们说了，就是基于物理的这种材质和光照模型呢，虽然可以模拟更多的物体，但是它也是有很多的参数的。然后这些参数通常呢是由贴图资源来承载的。那么如何去兼容美术制作的这个材质贴图，然后并且顺利的导入引擎进行渲染呢？这个也是一件非常重要的事情。现在主流的那个 PBR 贴图的制作软件是 Substance， 有 Substance Designer 和 Substance Painter。我们可以看到这个中间的这个节点集合，它会有很多输出的节点。然后在 Substance Painter 的右边，大家可以看到那一行可能字太小了。就那是一些输出的那些节点集合，这些节点集合其实就是我们 PBR 的这个模型所要用到的参数。那我们可以在这个软件里面去制作、去合成这样的贴图数据，去合成这样的参数数据。然后这个参数数据可以通过一个内置的 GOSIM 引擎对应的一个导出脚本来把它合并通道，并且导出，然后输出到不同的贴图里面。然后在引擎内呢，我们可以支持对这种导出贴图的集合和这种导出贴图的集合文件夹进行一个自动的材质创建。然后我们会根据这个贴图去自动搜索使用合适的 shader， 然后把这些数据绑定在这个材质里。那这样的话，开发者可以更容易的在这个材质制作软件和引擎之间去同步它的资源。那除了这个 SP 的贴图之外呢，用建模软件制作导出的这种 GLTF 的模型，它本身里面也是含有材质的。那么 GLTF 的标准的材质其实就是基于 PBR 的。我们可以看到它有固有色，然后金属性粗糙度和 AO， 还有法线图等等。那同样的，它也有一个扩展，就是 GLTF 的扩展是来支持我们刚才提到那些高级的材质，比如说各项异性或者是清漆、内反射或者是穿透这样。那除了 GLTF 的模型之外呢，我们也是支持 FBX 的这个模型格式。FBX 其实用的是比 GLTF 要更广泛的，那么它里面的材质会更繁杂一些，因为不同建模软件导出的 FBX 材质其实差别很大的。有的导出是带 PBR 的，有的导出就直接丢掉了，然后 fallback 回老式的那种光照参数。那根据这种不同建模软件导出的这种问题呢，就是很多小的团队和独立的开发者，他也不一定就是会去用 SP 的，他可能会自己简单的做一下，或者是网上随便下一些这种模型资源。那为了能够适配这种现象，就是尽可能多种类的格式和模型文件呢，我们开发了一种智能材质转换的算法，然后它可以动态的把老式的这种柏林缝或者是像高光、光滑度这样的 PBR 的工作流转换成引擎内部支持的这种金属性粗糙度的 PBR 工作流，然后它可以具有非常相似的光照表现。这样呢，既能适配用户的这种资源格式和材质，又能够避免引擎同时维护多套这个光照模型带来的成本消耗。这是一个案例，就是左边是用 Blender 做的一个模型，然后因为 Blender 只支持 PBR 的这套材质节点，但是它在导出 FBX 的时候，其实这些数据就丢掉了，它就会转成柏林缝的数据输出。如果不考虑的话，就会像右边的那张图一样，看起来很油腻，就是跟原来这个模型差别很大。然后经过了那个智能材质转换之后呢，它就会变成这样。 就非常的相似了。然后这个是酒馆的一个场景，酒馆是一个开源的一个场景，也是 FBX 的，然后它里面的材质也是老式的这种柏林缝。这个金属性和粗糙度的参数呢，都是通过智能材质转换动态转换的。然后它的光照效果一会儿会有一个视频，大家可以看得到。接下来我讲一下 shader。那 shader 是开发者在制作渲染表现的时候呢，经常需要面对的东西。所有的光照、材质还有着色的运算，都是要通过 shader 代码来进行的。那随着技术的发展呢，还有包括这种光照材质模型的迭代呢 ，shader 的代码也会变得越来越复杂。那考虑到 PBR 运算的这个复杂性呢，我们需要将整个流程要去分类、去解耦，然后尽可能的把这些流程呢封装起来，不要暴露给用户。这样的话可以降低用户的一个开发负担，然后也可以降低引擎的维护成本。但是同时我们又需要有一定的扩展性，比如说光照模型，我们也不是只支持了 PBR 一种，我们可能也要支持那个就是非真实性的，像卡通渲染这样子的光照模型。每一个模块是独立的，但是它又是可扩展的。那我们大致会把它拆成这3个模块，就是然后在最终的代码里把它根据选择去组合在一起。这样的话，它既有解耦，既能够解耦，然后又有扩展性。那第一个就是光照模型，光照模型会就按之前说的，就是它会根据材质的参数去做一些纯光照的、纯照明或者是阴影之类的计算。然后会有一个内部的一个通用的流程，就是那个 common 的 lighting flow， 然后会进行一个主光源或者是cluster 的光源剪裁。那接下来呢，这个光照模型对应的参数会在第2个模块，就是叫做表面参数，这个部分会开放给用户。然后我们也会提供一些内部的默认函数，就是如果用户不需要某一个参数的话，他就可以不写，这样的话它的维护成本就会更低。然后第3个就是我们之前的3个阶段里面第3种阶段，就是一个组合、一个着色的阶段，它会把前2个阶段的产出组合在一起，最终呈现那个渲染画面。我们把所有的计算都通用化、模块化、封装了之后呢，这样的好处是整个场景的光照结果是非常统一的，就不存在说有些物体用这个shader，然后有些物体用那个计算，这样的话整个场景可能你用同一盏光，它没有办法达到一个统一的效果，然后有些甚至出现，比如说我加一盏光，有些物体响应，有些物体又不响应，这就非常的麻烦。那在这种情况下，我们除了光照效果统一之外呢，也可以方便的加入一些附加的功能，比如说这种渲染调试啊之类的这功能。然后引擎在升级和维护的时候，也不需要考虑用户迁移，只需要对暴露给用户的这一部分接口不要变更，这样的话就可以放肆的在内部迭代就可以了。这是刚才讲的一个流程图，绿色的部分就是我们封装起来的，然后蓝色的这部分是暴露给用户的，然后 lighting model 那部分呢，我们可以计算就是像慢反射，然后高光，然后反射、折射、散射之类的这些数据，然后它会经过一个统一的流程到把它存到一个光照的结果里面，然后用户提供的这些材质参数会通过用户自己的一些 surface 的函数，然后也会保存到一个结构体里面，然后着色的这个模块会把这2部分组合起来，并最终输出。然后我们现在其实更关注用户这一部分的，所以我把这部分单独抽出来。这部分就是每一个那个参数它都可以对应一个函数，那也有一个最终的一个共享的一个函数，可以对所有的这些数据进行操作。比如说固有色，还有那个半透明上面那个，然后右边这个是法线图，下面的这个是散射的参数，左边的是 PBR 相关的这些参数，都是有一个函数去对应的。那用户就不需要关心任何其他的东西，他只需要在这里面去做，他需要采什么图或者需要去做什么计算就可以了，然后把这个参数输入到系统里，系统就可以自动去完成后面的计算。那有了这样的封装呢，我们就可以用可视化的方式去自动生成暴露给用户的刚才的那一部分函数代码。这个就是 shader graph， 然后它是一种类似于蓝图的节点式的一个编辑系统。那最终的每个输出节点呢，都是对应一个材质参数的。然后中间计算过程的每一个节点，它都可以预览，然后真正可以做到所见即所得。然后因为它非开发很灵活，它也不需要用户去懂代码，所以对美术也非常的友好。就是类似于这样子的流程。那中间的那些节点，就是给用户自己创建一些计算的节点，然后可以拖拽他们的计算顺序。然后最右边的那个节点集合，它是最终输出的那些参数集合。我们看一下这个对应关系。左边是 shader graph 的输出节点集合，然后右边是我们刚才提到的内部使用的参数集合。我就勾了几个典型的这个数据，其他的也没有勾，不然会很乱。然后跟代码的对应是这样的，左边是用 shader graph 自动生成的代码，然后它可以通过这样子的顺序把它传入到系统内部。那除了代码之外呢，在开发过程中调试其实也是非常非常重要的。然后现在的实时渲染呢，因为越来越复杂嘛，它可能有多光源，然后有阴影、烘焙啊、雾啊，还有 HDR 什么后期处理，很多很多元素叠在一起。那如果渲染效果不合预期的话，其实想找到问题是挺麻烦的，因为渲染效果这个东西它可能不太像这种普通我们写普通的 APP， 它错的就是错的。这个有可能，比如说颜色差一点，你去看这个值，它并不是完全错误的，但是你看起来效果就是有点问题。所以在这种情况下，我们也加入了就是渲染调试的一个功能。然后这个机制可以很方便的展示每一个小块我们想要的数据。大致上我们分了3部分，就是左边的这个是模型数据，比如说 UV， 然后有顶点色，还有就是模型本身的切空间。那中间的这个是材质数据，材质数据更多的是来源于美术制作的贴图吧，就比如说 PBR 的那些数据，还有就是法线图，经过法线图变换之后的这个切空间。那么通过前面这2个部分呢，美术就可以很容易的把出错的东西给挑出来了。比如说它有可能这个模型没有开切线，或者它的法线是有问题的，它就可以第一时间筛出来这个问题，然后它就可能把这个定位到资源系统本身的问题，那就不需要再往后面去查了。那如果这2个部分没有问题的话，还有第3部分就是中间光照的数据，比如说直接光的漫反射、直接光的镜面反射，还有环境光的漫反射和镜面反射，然后包括烘焙的光照图，然后阴影和 AO 这些都可以单独的去显示。除了这些单项选择之外，我们还提供了一些复选的方式，就是叫做组合模式。它是可以像 PS 一样那个图层一样，就是可以一层一层的叠上去的。这样的话就可以很容易的定位到是叠了哪一个功能之后出现的问题。可以看一下这个演示啊，这是那个酒馆的场景，这个是调试那个 CSM 的那个层级阴影的，可以看到每一层的着色。然后这个是模型数据，这是模型的法线。这个是 PBR 的数据，这属于材质参数。是半透明，因为一般只有植被，在这个场景里只有植被才有半透明，所以可以看到一些草啊、什么灌木之类的。然后这个是通过那个智能材质转换转出来的一些数据。现在是光照数据，就是纯光照，一部分一部分把光照拆出来，然后你可以看到太阳光的光照，然后或者环境光的光照。是 自发光，因为有一些灯泡的，在那个场景里面有一些灯泡的。好，这是阴影。然后环境光遮蔽。现在是恢复到正常的渲染状态，然后会用组合模式来调试，一层一层往上加。最后就剩了一些，就是像 HDR 或者是伽马矫正这样的颜色空间的操作，现在就又恢复到正常的样子。最后一部分我讲一下那个渲染管线。其实渲染管线是整个渲染系统的一个基础吧，就是所有的模型啊、贴图的资源，还有 shader 的代码都是需要管线去组织起来，然后按照它指定的顺序去渲染和调配资源的。GOSIM 的渲染管线叫做 Render Graph， 然后它是一个基于数据驱动的一个管线。那这样做最大的好处其实还是灵活，扩展性很强。然后对于上层的使用来说呢，它是非常非常容易的，因为用户只需要简单的去添加一些绘制以及指定每次绘制所对应的输出的数据就可以了。就是用户只需要想到自己上层的逻辑是什么，他不需要去关注说底层需要去注意哪些细节。那 Render Graph 会根据指定的这个上层的需求呢，自动去协调资源的读写，然后渲染的状态，还有一些渲染的顺序，这些对用户都是不可见的，用户也没有必要去关注。然后得益于这一点呢，就是它的一个高扩展性，我们甚至还做了一个就是类似于 Shader Graph 的一个节点式的编辑系统，然后用户可以自由的去创建绘制的节点，然后每个节点呢也都有自己的输入输出的依赖。然后可以看到这个每个节点都是可以创建出来的，然后每个节点都是一个 path， 就类似于后期处理的一个一个的这种 path。但是当然它能编辑的东西不只是后期处理的这种全屏的这种绘制 path， 它也可以编辑物体本身的绘制 path。那然后 Render Graph 所有东西都会根据这个 graph 这个图指定的这个顺序来自动的调配资源。然后用户就可以更加聚焦在实现自己的需求上，甚至说他也不需要懂代码，他都可以改变整个渲染管线的流程，然后去包括生成 shader， 然后生成渲染管线都是可以由用户自己去做的。同样，它也是所见即所得的。然后我们这有一个演示视频，就是大家可以看一下是怎么去改变那个拖拽那个节点之后，在场景里立刻生效的。本的顺序，然后他把 bloom 给断开了，然后场景里面就泛光就会消失。再把它连回来，泛光就有了。刚才说了，就是用户怎么去 DIY 一个渲染管线，然后当然我们也提供了一个默认的一个渲染管线，就是一个前向的渲染管线。就是你如果不做的话，就可以用我们提供的这套默认的。那首先是渲染依赖的数据，就是像什么 阴影图啊，或者是一些 cluster 的数据。然后接下来是到场景物体这一部分，就是左下角这一部分。然后先是不透明的物体，然后处理散射的计算，然后还有一些机身渲染，像什么 AO 啊，或者是延迟的雾之类的。然后最后是半透明的物体。接下来到右下角的那个抗锯齿的阶段，然后做完之后进入到后期处理的效果，像泛光或者是 LUT 或者是超分这样子。那绿色的这些节点呢，它都是用户可以自动，就是可以非常方便的去移除或者是添加的，因为它是一个组件式的编辑。左边这个黄色的是我们内部写死的，这个是不能改的。但是绿色的部分都是可以动态的添加或者是disable 或者是 enable 这样的。这是我们支持的一些后期处理。然后第一个就是抗锯齿，因为左边的那个其实锯齿很多，就是在这种场景下面，它有很多这种平行的这种线，然后它的尤其在移动的时候，它的锯齿会特别明显。然后可以看到左右的对比，这是时间性抗锯齿的一个效果。然后接下来是超分辨率，然后现在也比较火，就是它可以用更小的计算量，然后来完成更清晰的一个画面。这个是泛光，就可以看到那个霓虹灯牌上面的一些泛光。接下来是 AO， 因为很多像室内场景的话，它基本上都在阴影里面，就在太阳光的阴影里面，那么它是非常的没有层次感的。然后它需要一个环境光的一个遮蔽，让它产生一些明暗的对比。所以我们也加了一个后期的 HBAO 来完成这个事情。这是可以看到那个地毯，就那个地毯挂毯，是那个下面的那些。有了明暗的层次之后，整个场景看起来质感也会好一些。这个是计算的纯遮挡的这个信息，是白膜的信息，然后把它应用在上面。最后给大家看一下一个赛博朋克场景的 demo 吧，它融合了我们最新的一个光照和材质计算，然后渲染管线，还有后期的一些效果，然后对开发者来说也是一个完整的示例。这是 cluster 的多光源裁剪，这个是反射探针。这是渲染调试。感兴趣的同学可以扫码关注一下我们的公众号，谢谢大家。
Yeah, thank you, Jin. It was amazing presentation. It's quite incredible what you can create with the Cocos Creator. So, do we have any questions? And of course, you can ask in Chinese. So.
感谢您的分享。我对Cocos 引擎的那个 Render Graph 比较感兴趣，然后想知道它的扩展性怎么样。比如说，如果我想自己做一个 Fast Forward 这样的绘制流程，然后想要引入一个计算的 pass， 比如说对场景中的所有光源进行一个裁剪之类的， 然后再引入一些渲染资源，比如说这个计算 path 它会生成一个类似于 storage image 之类的这样的资源，然后这个资源能不能加入到render graph 已经提供的那些 path 的节点中插入进去啊？
这个是可以的，因为其实 render graph 是一个更偏向于底层的，而不是偏向上层应用的，所以其实它更多的是一种资源的一个动态组织，然后像你提到的这些东西，都是相对要上层一点的一个应用嘛，所以它底层会去自动帮你去适配，然后你只需要把你比如说你产出那个 image 的那个 path， 然后指定给它添加进去，然后把需要产出和输入的这个 image 的名称提供好，它会自动会根据名称去对应，然后它会在后续去自动组织你的这些资源的输出和输入的。
好，谢谢。
你好，我有个问题，就是看您提到了那个，就是有很多在那个 debug，就是渲染效果方面，比如说显示它的法线啊，或者是光照这些东西。然后想问的是，就是维护这样一个大的仓库，在多人协作的时候，比如说我们传统通过 CI/CD 做，比如说有 code review 啊，或者是单元测试，就是有没有另外一些其他的自动化测试方案，就是在这个里面。然后像针对动画的话，就是这种场景，比如说动画它可能更复杂一点，它有交互啊，也有那些状态不同的状态这种流转这个方面有没有一些自动化测试的东西？
我们引擎团队内部的测试是有这样子的自动化案例的，就是动画它会去根据第几帧，它会根据那第几帧去截，然后根据第几帧的这个截图去做图像的对比，然后这个图像对比当然也是有一定容错的，就是也可能不要求完全每个像素都要一致，但是基本上就是按照帧数来算的话，它会在指定的那一帧会触发，然后去截出来。基本上我们现在这个流程都已经在走这种大规模的自动化测试，但是这个和渲染调试好像没有啥关系，渲染调试主要还是在开发材质的时候使用的。你说的这个应该是属于测试的流程。
对，就是说，比如说我，就多人开发的时候，比如说我发起 merge request 的时候，你做了 code review， 跑完单测之后，就是这个过程它有没有什么自动化测试？比如说我要 merge 这段代码，可能会引入一些新的问题，那有没有一些自动化的测试在这个里面？
我们内部是有一些指定用例的测试的，然后会有一些效果参考图。如果你 merge 了这个代码，然后它根据这个代码新跑了一个测试用例，然后发现和指定的参考图不一致的话，它会报错的。然后你可以点进去看具体的就是 detail 是哪里有问题，哪些用例有问题，这样。
就还有一个问题就是那个 DCC 软件，就是不同的那个软件，比如说 3D Max 或者是玛雅，然后还有它不同版本，比如说像 FB 和那个OBJ 转 GLTF 的时候，它经常会有那种贴图通道丢失啊这些问题，就是有没有什么好的方案或者是工具？
这些我们就是也是根据用户的反馈，然后可能会在导入器里面做一些 hack。其实像Unity 或者是 UE， 尤其是 Unreal 啊，他们做的这种针对资源和美术的 hack 是非常非常多的。然后所以他们可能就是这种方面积攒的经验也会更多一些。有些东西其实也很难处理的，就是它就是丢了，然后你要想尽办法让它能够不要表现得太明显。就是这个可能是得根据实际的，比如说具体的某些事情来做。对，然后
就这个过程中可能也需要美术的介入。
是的，是的，就是需要用户去报，然后可能美术要去分析是什么情况下会丢，然后有些问题，可能会有一定的普适性，那我们会去专门去处理。但有些问题没有普适性，可能就不管了，因为如果你处理了这边，很有可能会就是两头按下葫芦起了瓢，可能其他地方也会不对，所以也会有这样的考量。
好的，谢谢。
你好，金老师，我也是对那个 render graph 比较感兴趣，就是我看你们那个都是节点写好，还有一些是已经封装好的，然后这样会不会导致丢失了一些那个扩展性啊？就是有没有那个自定义节点的功能？
其实你可以完全的去写这个代码的，就是代码你可以去写，只是因为有一些人他可能不一定代码基础很好，然后所以提供了这个方便的这个功能。但是，Random Graph 是一个非常灵活的，就是它本身就是鼓励你去用代码完全去把它取代掉，它只负责底层的一个组织，然后你所有的上层需求，就是哪怕深入到像比刚才那个同学问的还要更灵活的这种用法，你都是可以通过代码去写的，而且它本身就是一个脚本，它就是个脚本语言的东西。你去创建一个脚本，然后来组织你的场景结构，包括怎么画每一个物体，然后包括你中间要插什么 path， 需要生成什么数据，都是完全自由的。它其实更偏底层，它不会影响你上层的这个逻辑限制的。
好的。
So do we have any other questions? Anyone? All right. Thank you, Jin. Thank you so much.
谢谢大家。
Yeah, so this actually concludes the day, the workshop. So thank you everyone for joining this workshop for the 2 days. I really hope you enjoyed coming here, and it's been 2 great days, I think, for everyone. So thank you so much for joining. Thank you.